喂，
帮我叫他的操作者来。全部放下。
哎爸，摄影师大哥叫我去找顺，能过去。喂，
你一定不是，就是先秀一张，至少让大家知道他们来对比的。下次你要先插上去再吹，对，否则这个会有时候会上。对，你重新先。因为刚刚你已经进 display mode，有时候会 screw up 的那个。就，对。所以有时候你看等很久，就是有 something is wrong。不是，这个我们一天到晚要处理这个是。这个名牌我刚刚还没应该。
Yeah, we can do that. Yeah, sure. Yeah. 哎，婷佑，他的档案在你那边。谢谢。How are you?
Hi, good morning. Good. How are you? Full of energy.
Hopefully, we'll see how that goes. May I know if this video contains any like videos?
No, I'm just more worried about the fonts. Because sometimes yeah, it's fine. No, see, there is a problem with the fonts. That's what yeah, the fonts are off. You guys don't have the font that I'm using. Can I use my machine?
Yeah, sure.
Yeah, let me grab my machine. wrong, right?
Yeah.
I don't know. The problem is like when I use their machine, the resolution is fine, but
Maybe we can adjust it on your desktop. We can change the resolution of the second screen.
另外一台电脑上。这种东西最麻烦。
你也帮我看一下附近的地板有没有？找到了，找到了。
那就可以。好，这是你的地盘。
Hello. Hi. In the interest of time, we have a fully packed schedule, so I'm trying to open on time, even though we are already 3 minutes late. Okay, but first of all, welcome to National Taiwan University to attend the 2019 IOX workshop. And we're very happy to have this opportunity to share many of our exciting research with everyone, both academic and industry in Taiwan. And so because we have a kind of a unfamiliar name, so I think my responsibility is trying to explain, first of all, what is augmented collective beings. Okay, so instead of giving you a lot of slides, just imagine in the world of all these new intelligent machines, many people will have difficulty understanding what the machines are doing, why the machines are making particular decisions, and how to change or affect the behavior of the machines. And because of that, we have started a project 5 years ago. We started a proposal, and we actually started a collaboration with Intel, Delta Electronics, and Compo in this endeavor, trying to explore technologies that will augment human capabilities to improve this particular interaction. And in particular, this domain, we rely heavily on technologies in artificial intelligence, IoT, as well as human-computer interaction. So we do include experts on interaction design and human studies. So today, I'm going to kind of start by just talking briefly in order to help people interact with the smart machines. Our center, we focus in particular on a lot of the techniques for sensing and cognition and interaction. So here is the particular goal, kind of a picture of our different technology. So some of our technology aims to improve the sensing, so we call them super sensing, and some of our technologies aims to improve our understanding or cognitive capabilities of our surroundings. So those are the supercognition. And some of our technologies aimed at improving communication between human and machines, as well as machines and humans and human, everybody. So in fact, the word of beings include both machine and people, and maybe even abstract objects in the future. So this is kind of the basic frame of our technology vision. And because of our collaboration with the industry, 3 years ago, we started focusing on maybe particular use case where we can demonstrate this type of technology. So we zoom in on the idea of a smart workspace. So many of you come from a manufacturing setting. This is very familiar, that in a factory setting, you may need to be able to work with many automated machines. So in fact, recent many kind of stories and cases demonstrated that even though a lot of people would like to have fully automated manufacturing, but it is actually not easy to achieve that. And in fact, it is not even desirable to do full automation because a lot of work may still rely on human insights. So in fact, it is important to enable people to work with large number of heterogeneous smart machines. So this is what we are trying to do. But in fact, smart workspaces include not just manufacturing settings. It could be any industry, or it could be just as simple as a personal workspace. So many of the ideas we hope that will carry through, not just in a particular domain, even though some of our work use manufacturing as an example. So in this particular simple illustration, so in fact, in our center, we also try to do cross-interdisciplinary research in the sense that many of our research problems are not defined from a purely technological point of view. So we work with designers who, by trying to understand existing technology, trying to envision what these technology can bring and may bring to new possible ways of deploying these technologies. And then we use those visions to help technical people in focusing their particular solutions. So in this case, on the left-hand side, given that we will be deploying a large number of all kinds of sensing devices, so for example, cameras, touch sensing, light sensors, and all kinds of different sensors in a workspace, we try to see how with all the different heterogeneous sensors we'll be able to monitor many activities in the space. So for example, one of our talk this morning will be talking about distributed intelligence, where we will be able to track human activities with multiple cameras. And additionally, we also have this idea of like a machine coach, where you will be able to capture knowledge and skills from experienced workers and trying to guide inexperienced workers when they first started learning the trade. So many of these issues may center around monitoring the awareness of the workers as well as the wellness of the machines. And maybe, like as I said, for transferring knowledge and skills in job training situation, and also in error prevention, or in archiving the important knowledge for the particular company. So in today's talk, you'll be hearing many of the different subjects, and also in the afternoon, you'll have the opportunity to see many of our demos. So in this particular case, we will have a demo illustrating smart task space where we are able to showcase different technologies in touch interactions with workers and machines, and also interactive dialogue in helping users while they are trying to perform a particular task, or interactive machine learning where they will be able to understand, personalize the particular user being monitored. And we also incorporate some design, in particular in lighting interaction of the environment with the workers within this particular environment. So I think some of you might have seen this particular video, but this is kind of a concept where we want to be able to showcase this technology. Oh, so this voice did not come out. So audio feed 没有。So, okay. So the idea is that with all these sensors, we are able to use this particular proxy task of assembly a mechanoid robot, which contains hundreds of parts. And in fact, if you are going to do it for the first time, it may take more than 10 hours to assemble this particular robot. But the idea is that we want to be able to help people monitor the particular case. And so for example, when this worker is trying to do a particular thing, and by reading the instructions, he needs a particular size of a screw. But when a novice worker may have a hard time trying to tell one screw from another. So it's very difficult to say if this is an 8mm screw or 6mm screw. So our system will be able to trying to help the user in understanding the task. So I think many of these will be showcased in our demo. So I'm not going to go through the entire video since the audio didn't come out. So, but you should be able to see many of our demo videos on the website of our center, NtuEE70th Center. So in this particular view, you will see we want to be able to interact with the user, not just by camera, but also with voice, dialogue, and also with lighting. Okay, so this doesn't work. And also, another group of our demos will be talking about a smart factory. In particular, you will see a mobile robot have the ability to be able to do tracking and kind of following work, collaborating with a human. So in this particular set of demos, you will be able to see the multi-camera tracking as well as a recall tracking, which is using a single mobile camera. So without taking too much time, my task is just trying to introduce the program so you kind of have a overall view. So this morning, we're very happy that we will have 4 very different talks, and we will start with a keynote by our long-term collaborator from Intel Lab. And later I will do the introduction. And also we will have 3 different talks. And in the afternoon, there are 2 different sessions, and also there are parallel demos. So from 1:30 to 3, you will have a few talks that will be delivered in Chinese, to accommodate many of people who prefer a Chinese presentation. And in the second half of the presentations, we'll have a series of tech talks that will highlight many kind of the most new topic and advanced technology that are being developed in our lab. And at the same time, if you prefer going to the demos, you will have the opportunity to see the open house. So I think with this opportunity, I would like to thank all our sponsors, Ministry of Science and Technology, National Taiwan University, Intel, Delta, and Compo. But my most important task is as a bridge to the keynote for today. We are so happy not only have the opportunity to collaborate with Intel, and Intel has 6 delegates coming all the way from the US today. So we are very happy to have the Intel fellow, Lama Nachman, to give a talk on liberating technologies to venture into the real world. So Lama leads the group on anticipatory computing, and her interest is in ubiquitous computing, sensor network, embedded systems, predictive and assistive technologies. And so I think I'll let her talk about many of her interesting projects. But I do want the kind of plug that, not only she is a very, very strong technical person, but she has a very keen insights on many problems that will directly impact human lives. And I think those are very important vision for guiding the most interesting research problems that we are undergoing at this point. So without further ado, let me introduce Lama. 所以要换电脑吗？ Okay. So what are you trying to do? Oh, no. The projector is a bit slow in sensing. Okay, cool. So you want?
All right. I'm just going to keep this here so I know what time it is. Pointer. All right, awesome. Okay, can you guys hear me? Awesome. Well, first of all, thank you, Jane, for the very kind introduction. I'm actually quite honored to be here and talk to all of you today. One thing I want to say before I start talking about the topic of this talk is to really comment on the amazing work that's happening in the center. And for me, there's something really strategic about the work that's happening here. So when I think about where AI is headed and where a lot of focus is on automating people out of the equation, one of the things that I really love about the center is it's really focused on trying to bring people back into the loop and thinking about how AI could be utilized to really amplify human potential and really utilize the notion of human-machine collaboration, and recognizing that there are strengths that each side brings to the table. And I think that's from a strategic perspective and from a long-term perspective, that's really the way to go. So I would really urge you to listen to all of the talks, come to all the demos, because really the work that's happening here is cutting edge and really just extremely on point. So I'm going to take this a bit in a direction that might be a bit controversial. I tried a version of this talk at UbiComp a couple of months ago, and so we'll see what happens here. But basically, the higher end point that I'm really trying to make here is that, we all are excited about cutting edge research and all the things that we want to do. And the potential for AI and ubiquitous computing is really huge. And it can make impact into people's lives today. However, I would make the argument that I see people leave things way too early in the research phase and not really spend the effort to understand what it takes to actually take technology into the real world. And as a result, what we put out are things that are brittle, that are not scalable, and we have this notion that the rest is engineering work. And I'm really hoping that maybe I can convince you that that's not true, and that there is tons of interesting research to be had when you actually think about the real world and what it takes to actually take technology to impact people's lives. So you don't have to give up, publishing in top venues just because you want to make your technology deployable into the real world. So it's controversial, but we'll see how it goes. So I'm guessing I don't really need to convince this community that sensing has become ubiquitous in the world, right? It clearly started with mobile phones being ubiquitous and bringing sensing to every human. But then, later on we've seen an amazing rise in wearable devices and getting more intimate type of sensing enabled. And, I think one thing that I should do is just update the slide and put the rise in home assistant technologies, Alexas and Google Home and so on. But clearly there is no question that we have gotten to, to a point where sensing is ubiquitous. However, I would make the argument that while sensing has become ubiquitous, it really has not utilized its full potential. And the reason I say this is that if you think about what people need of technology, and whether through a lot of the ethnographic work that we did, or the ethnographic work that has been done, out in the external world, there's, while people have different expectations of technologies and what they want technologies to do for them, I would argue that there are a set of human needs and desires that tend to be common across these different responses and things that we hear back. And so I try to kind of summarize them in these four, right? So I would argue that people want technology to be truly personal, that understand their very specific needs and personalize to that. They don't want technologies to be just the same, right? My own technology should look very different than yours, just in the same way that someone that you spend a lot of time with will actually understand you much better over time. People also want to be unburdened, and today technology is a burden, right? We have to take care of it, we have to charge it, we have to remember passwords, we have to become the IT people for our own technology, instead of actually it unburdening us. People also want technology to keep them in the flow. And if you think about what happens today, you're bombarded constantly by tons of information that most of the time is totally irrelevant. So instead of working in the background to understand what's relevant in the moment, understand your context, and bring you things, really be mindful and considerate of your attention in some sense, right? And then finally, I would say people want technology to enable them to be their best selves, right? So how can technology enable me to be the best researcher that I can be, the best manager that I can be, the best mom that I can be? And clearly technology is far away from that. So if I try to think about kind of the different ways that technologies or smart technologies interact with us, I would say you can think of a spectrum. So on one end of that spectrum, we have technologies that are broad in nature. So if you think about an Alexa, a Siri, it can help you with quite a bit of different things, right? It's, and skills continue to improve over time, and that range or breadth of that technology continues to improve. However, it's quite reactive in nature, right? You have to tell it what you want out of it. You have to ask it a question. You have to supply that context. It's not going to come in and just tell you what it thinks you should be doing or give you something helpful. Contrast that with this other end of the spectrum, which is something similar to a location-aware technology, where, for example, you get in your car and your phone will tell you something meaningful. It might tell you that, oh, it will take you X amount of time to reach your destination, or there's an accident on your way, or whatever it is. Now, you didn't tell it your destination. You didn't even tell it you're getting in the car and starting to drive. It figured that out on its own, and it said something that's reasonable. And, I would say that the only reason this was possible and Google could make that happen is because they invested more than a decade understanding everything that has to do with location. Turn-by-turn directions, points of interest, location prediction, all of these different things really needed to come together to be able to say something sensible in a proactive way. And the reason is, it's very, very easy to get this wrong. And I'm pretty sure we all remember some of the earlier technologies, whether it's Clippy or, all of these things that were trying to be helpful and they were not helpful at all. So really what my point is ideally what we would want is something with the breadth of what's on the left, but with the proactiveness of what's on the right. And that's really what would enable a lot of these things that I talked about in the previous slide. So what is preventing us from getting there? I would argue that what's preventing us from getting there is actually robust perception and understanding across all of these different areas. So, which brings me to what we're trying to do. So I am quite lucky to run the Anticipatory Computing Lab, which is an amazing group of multidisciplinary researchers that span ethnography, design, and technology. And we're working to try to really figure out what type of technologies, utilizing sensing and sense-making, that could really help people in everyday settings and help amplify that human potential. So everything that we do starts with an understanding of users, what the gaps are, what they're trying to do with their lives, and then try to get out of that an understanding of what types of technologies are needed and at what fidelity is that technology needed. When we talk about a recognition accuracy of X, what are we trying to get to, right? Is it meaningful to improve accuracy by 0.2%? I would argue it's only meaningful if that enables you to do something that you were not able to do before. So you need to understand what is the bar of that accuracy and fidelity that is needed to enable a specific experience. And for the same capability, it might be something different depending on what experience you're trying to enable, right? If you're trying to use a recognition technology to log you into a bank account, that would look very different than if Alexa is trying to personalize your music experience. So a lot of what we do is really centered there. And in many cases, yes, we do utilize a lot of open data sets to try to build all sorts of capabilities, but most of the time we actually have to get our hands dirty and collect our own data sets because a lot of these, type of data sets are not just available in the wild. We actually focus quite a bit on multimodality because we do believe that to get things to be robust in the real world, you actually need to have multiple modalities coming together. And that is both for improving accuracy and robustness, but also for improving coverage. And then I'll just say this, since every single time I give this presentation, usually the first question that I get, and why does Intel care? Isn't Intel a silicon company? So I'll just explain why we're relevant to Intel. So we're relevant to Intel in multiple ways, right? So one is, if you're trying to really understand where technology is headed and what type of things we will be running on these platforms in 5 years from now, then we really need to be doing all of this work, right? Because we don't want to be building silicon for what is running on it today, but we want to be building silicon for what will run on it in 5 years from now. Also, if you think about what it takes to actually bring solutions out to the market, at the end of the day, time to market really matters. And having all of these capabilities optimized on Intel silicon that we get out in the real world means that people can actually build on Intel much faster. So that's why we are relevant to Intel. So basically, the way that we think about this is we think of different types of applications and verticals. So that's the stuff that's on the top. So we look at things like smart home, education, smart manufacturing, etc. And then from there, we go in and try to understand, well, what are those capabilities, right? What are those things that we need the machine to be smarter about and understand about the humans? So whether it's understanding activities, understanding who the user is, understanding intents or emotions or engagement and so on. Those capabilities really are the ones that would go enable those different verticals. So it's not necessarily about building one specific vertical, but it's really trying to build the platform of capabilities that will allow people to innovate on top of this. And then there is kind of more basic capabilities under all of these things that I have in the middle that are just more foundational in nature, right? So, for example, some of the work that we're doing on probabilistic computing to try to actually enable these type of technologies to come to life. And I'll talk a little bit about that. Okay, so I'll give some examples of some of these horizontals and why we've chosen to focus on the pieces that we've chosen to focus on, just to maybe give you just a better sense of what I mean by robust and why these things matter. So let's take the example of user identification, right? Which is, you would think is kind of a basic capability. If we want to try to personalize any experience, then we should start by understanding who the user is. So, one could ask, well, why is this even an unsolved problem, right? I mean, we all have a phone today. I use, the face recognition on my iPhone all the time. And if you think about that, going back to the point I was trying to make, what are we doing with this, right? We're trying to actually position this thing in a way that this thing can really understand who we are. And this is a much simpler problem. But it's actually a problem that the way that this has been solved works perfectly for this specific usage. Now try to think about what happens in smart environments and you happen to have a camera and a microphone somewhere within the room and there are all of these people that are in and out of view and all of these things. That gets much more complex. So one of the things that I talked about earlier is trying to utilize multimodality and the fusion of vision and audio, for example, to improve that. But one of the things that you might want to think about is, well, if I want to make this deployable in the real world, how do I do this, right? I mean, the burden of trying to train all of this, speaker model and audio from every speaker to make that happen becomes, a bit cumbersome and unreal and unscalable. So one of the things, for example, that we've been looking at is, well, can you actually utilize something like lip activity detection and vision to try to understand when a speaker is speaking and automatically segment that speech so that you can actually train a speaker model automatically, which becomes more of a scalable approach. We also, think about, well, how would this thing work in realistic environments in terms of noise and so on, right? So one of the things which I'm referencing here, the invariant representation learning, is trying to really learn a representation for both the clean and the noisy data and force the network to really have a similar representation for both of these so that you're actually bringing about a speaker model that is much more robust to noise. Now, there are a lot of other things that are happening within the center that actually are quite interesting in terms of pushing that forward and creating that robust recognition. So I would really encourage you to actually see Shawi's presentation and specifically looking at the re-identification across multiple cameras and how that actually starts to make these things robust in the real world. As well as Hong Yi's presentation where you're actually, one of the things that actually starts to solve the problem is really learning from a much, much smaller data set, right? And some of his work in that space is really cutting edge as well. Okay, another example that I'll talk about is activity recognition. So if you think about activity recognition, again, it really lends itself well to multimodality because if you think about it, right, I mean, when humans are trying to recognize activities, there are a lot of different factors coming in, right? We know something from the scene, we know something from listening to the background audio, we know something from interactions with RFID objects and so on. And, trying to bring all of these together into a multimodal recognition system is not really a simple thing to do. So one of the areas that we've been looking at is actually utilizing Bayesian deep learning to try to understand the certainty in each of the modalities and figuring out how you would fuse these modalities together to actually enable a more robust recognition. Another example, so this is actually an interesting approach to try to again, if you want to try to scale into the real world, the notion of what objects are people interacting with, one of the things that we've recognized is that RFID signals, when people are interacting with RFID tags, they end up disrupting that signal because of the fact that they are interacting with these objects. As a result, one could think about this as a signal on its own right and train models that can actually understand that disruption in both the RSSI and the phase to actually detect that something is being interacted with. So again, to make the point of what is happening in a controlled setting versus the real world. So initially, we were able to show this and show a proof of concept that has 50 tags in a space, and it can interact with all of these tags, and we can figure that out, we can reconstruct the signal, etc. Now, what happens in an actual retail scenario? Right? You have thousands of tags. You don't have 50 tags in a retail scenario. And that is one of the most compelling usages of object interaction, right? I mean, you want to understand what items people are interacting with in a retail scenario. So you try to do this with 1,000 tags. Now, if anyone knows like what the read rate on an RFID reader is, we're talking about 1,000 hertz to 1,500 hertz. So now you don't have enough samples from all of the tags to be able to reconstruct the phase and to figure out what this is, right? So as a result, a lot of the research that we've done in that space is like, how do you actually scale this? From trying to understand how to get into nonlinearity in phase and understanding that without having to actually reconstruct the phase because you don't have enough data to actually do that. And then I'll also talk about multimodal interactions, which is kind of an area that's really quite dear to my heart. And in this specific case, we've been really looking at how can we change the interaction in the case of kids trying to kind of learn different concepts. In this specific case, it was really around math. But one of the issues that we have seen specifically in a lot of the ethnographic research that we've done is that parents are actually quite concerned about screen time. And while parents do recognize that technology can bring a lot to kids' learning, they don't want that to end up they're rightfully so concerned about screen time. So one of the areas that we've been looking at is, well, can we think about some interactive agents that are projected in space, that understand that space, that allow kids to interact with the physical environment and learn different concepts, math being one of them, and we're actually working with a school in Oregon to actually push that concept forward. But now try to think about, how do you make an agent communicate with kids? I mean, I don't know how many of you have kids, but kids interact in a very interesting way, and they use all sorts of different things beyond words to communicate, right? So now when you start to build an agent like that, you really need to be cognizant of all of these different modalities. You need to understand, what they're pointing at, gesture and gaze and emotions and all of these different things to actually enable that type of interaction. And you need to be very cognizant of the specific dialogue that you're trying to enable in extremely limited dialogue examples. So that's the work that we've been really focused on this space. And then finally, I'll mention one last thing, which is emotion recognition. And I think that's an area that we will be working on for the rest of our lives, because I think it will continue to be an unsolved problem. But again, a really great example where there is no way that you can solve this problem without multimodality. And part of that is every modality brings something else to the table, right? So we know that from vision and text, we can get something about valence, and we know that from audio and physiology, we can understand something about arousal. So we really need all of these modalities together, not only to bring robustness, but to actually get us into the real, the actual emotions. So one of the things that we've been looking at here is actually, how do you then fuse all of these modalities across, how do you fuse across these modalities? And some of the work that we've done here is really learning different LSTMs for each of the modality, and then using the activation information from each of those to actually create yet another LSTM model that can not only understand the temporal information across in a specific modality, but also learn that across the modalities. Now, what's interesting about emotion recognition is that beyond the fact that it's kind of hard to understand how would you recognize these things, it's also a problem because we don't even understand what the ground truth is most of the time. So, this is one great example of how technology in the lab can get to really high accuracy numbers, but then once you put it in the real world, everything kind of breaks down, right? I mean, we can get, something above 90% accuracy, even just from physiology alone, in a controlled setting, but put it in the real world, and then you're at chance, basically. So, part of the problem in the real world is figuring out what is that ground truth in the real world, right? So, when we actually go and collect all of that data in the real world to be able to build these models, what we're actually doing is playing detective, right? So we're trying to get as much information as possible and try to reconstruct somebody's experience in the real world back to infer what type of emotion somebody had at what point in time so that we can segment that data and train it with this information. So it's definitely not a simple problem. Okay. So I talked about, some of the capabilities that we're building. Let me talk a little bit about some of the verticals that we're looking at. So, Jane talked about smart manufacturing, and it's definitely an area that we're working on quite a bit, and specifically, knowing that Intel is a manufacturing company. So we actually try to utilize that in our own, trying to understand from our own manufacturing process. We also have done a lot of work in trying to understand the state of passengers within vehicles. So when we talk about, again, having autonomous vehicles, the driver in the car does much more than just driving. The driver in the car is actually communicating with other people that are in the car. So once you take that driver out of the car, how can you actually interact with the passengers, and what do you need to understand about the state of the passenger autonomously? So that's part of the work. So I'm not going to talk about these two. I'm going to dig deeper into the smart education, and then talk about some of the assistive computing work that we're doing. So, education. Clearly, I would argue that education is one of those areas that needs major disruption. We really have not changed much the way that we educate. And we know that education is one of the most important areas, yet we have a very hard time scaling it. We have a very hard time making it equitable, have the right resources. Teachers are continuously overburdened and undersupported. So again, to make the point very clear here, this is not about taking teachers out of the loop, but empowering teachers with technology and AI. So one of the things that we know is you really need to personalize the learning experience because we all learn very differently. The other thing that we know, which we don't need to do our own research in, is that learning outcomes correlate with engagement. We know that from education research, right? So one of the things that we were trying to figure out is, can technology understand student engagement and then utilize that to personalize that learning experience? So one of the things, so this is work that was done in our Turkey lab and then now moved into the US, but this is something that we've been on for more than 5 years now. And, just like, again, taking technologies into the real world, you have to go into these real environments, you have to collect relevant data, you have to try to train these things, figure out what is it that you even need to recognize and what is relevant in these settings, and continue to actually, not only understand how well are your models work, but what does it, at the end of the day, is it actually enabling a better experience, and how can the teacher be empowered with this information? So that's been definitely an evolution with many, many deployments in schools. So basically, if you think about this specific problem, this is about students actually using content platforms in the classroom, right? So one of the interesting problems that happens when you do that is now there is a screen between the teacher and the student. So, it's really hard for the teacher to operate in that environment. So what they end up doing is they're really circling around trying to figure out what is going on and figuring out, how to help the students. So what we were trying to do is figure out, well, can we, from that platform, both from the camera sitting in that machine, as well as from the data that we can extract from the content platform, whether people are actually consuming content or doing tests or wherever, can we get enough information to understand the engagement of the student? Now, once you understand the engagement, you could either utilize that to help the teacher, accomplish, or help the teacher help the students. You can actually give that information to the students themselves, especially if you're looking at, older students. And you could also automatically personalize the content platform to actually take advantage of that. So this is the kind of what we ended up doing, is actually detecting the engagement from all of these machines and then giving the teacher an idea of what's actually going on in the class, so that then the teacher can intervene. Now, what's and this is something that we've published in Kai. So if you want to look at the results, it's there. But I'll just highlight one part of that, which is if you actually look at the teacher interventions, you could see kind of really an interesting difference in the control group versus the treatment group, right? So if you look at the top, basically the close monitoring is, imagine the teachers are hovering around trying to figure out what's going on, right? And you see a major reduction of that behavior. And then you see a major increase in the scaffolding, right? So the teacher's time is going away from hovering and trying to figure out what's going on to actually helping the students, with the task and things that are really struggling with. As we move to other environments, so this is, in some places you'll see kids, sitting in front of machines on their own desks, but, more and more we're starting to see these type of environments. So one of the areas that we've been looking at is, how a lot of the ambient sensing and understanding, and how do you start to define engagement in a setting that looks like that, right? So that's quite different than what you would see in that example. So that's the first one. The second one that I want to talk about is the work that we've done on assistive computing. And this is, by far, I think, one of the most meaningful projects that I've ever worked on. So basically, this goes back to, I think, end of 2011, when Professor Stephen Hawking basically approached Intel to see if there's something that we could do to help him communicate. And the reason for that is Intel had been supporting Professor Hawking with his computing needs. It's a commitment that we have made to him, for decades, and people were doing that, specifically setting up machines for him and making sure that he's enabled by the latest and greatest technology. However, when he came to us this time, or in 2011, it was really about recognizing that the system that he's been using, it has nothing to do with the power of his machine, but he's unable to actually control the system. So, we went out there and we tried to understand what is going on, what can we do about it, what is the problem? And the thing that to us was actually fascinating, here you have the most brilliant brain on the planet using an extremely outdated technology, which kind of totally baffled all of us, right? So we're like, oh my God, there's so much technology that we can bring to the table. And or if we can only, get him to use the latest gaze tracking, and, maybe we don't need to build anything, right? We'll just, and, in retrospect, we should have probably thought about, I'm sure that, Stephen knows about all of these different things, but we're like, oh my God, he's using something old. Maybe that's all we need to do. And, we were researchers trying to solve that problem, right? So it's not like Intel does any, products in the space. So we're just trying to figure out how can we help him. And then over time, as we started to test all of these different technologies that were available on the market, we've realized how off mark we were. Clearly he is the most brilliant brain on the planet, and everybody else wants to help him. So one of the key insights that we had is, at some point, his technical assistant asked me to come with him. And he's like, let me show you something. And he opens this closet. And that closet has everything, like brain-computer interface, gaze tracking, every technology. It was like, really amazing technology. And he says, this is where all technology comes to die. That was like his statement. And basically, his point is, there are all of these different companies and all of these different people that tried to get him to use their technology. And they were all unsuccessful because they tried to force him to fit into their technology. And that's not what he really wanted. What he wanted, given the fact that he depended on this technology to do everything, that was his lifeline. He wanted something that felt, familiar, but that improved his ability to communicate. He didn't want to revamp everything about this technology. And in fact, ultimately, it was about independence, right? He was trying to actually maintain the little bit of independence that he's had and not have to rely constantly on people to get his information, to communicate his thoughts, and so on. So, if you guys have not seen this before, basically this is what his system looks like, right? So, this is the old system that he was using. So basically, there's a software interface that runs on top of his machine, and basically imagine something that just highlights different things. So it's a time interface. And once the thing of interest is highlighted, he's going to do the equivalent of pushing a button, right? Clearly, Stephen cannot push a button because he can't use his hand. So actually, his technical assistant came up with this brilliant solution where there is that, what it calls a blink switch. It really has nothing to do with blinking. I don't even know why they call it a blink switch, but really what it is a proximity sensor. So every time he moved his cheek, the distance to that proximity sensor got much smaller, and as a result, the signal increased. Basic thresholding, analog, really quite primitive, but it worked. So every time he did that, essentially you can think about him pushing a button with his cheek, and that was his existing system. So, the problem is, what is hard to imagine is how unusable that is in a graphical user interface, right? Because now, ultimately, he's trying to scan a 2D space to select a point on a screen by literally, imagine a radar that just goes down this way and then this way until he hits the actual point of interest. So every time he needed to use the mouse, it was minutes of interaction. I mean, one specific example that we've timed was actually opening a file. So just imagine how many files. I mean, Stephen uses his machine in exactly the same way that we use our machines, right? I mean, he does everything with it. He teaches, he reads, he explores, the internet. He writes documents and books and so on. So every time he opened the file, it took him 4 minutes. Just imagine that, right? The most brilliant mind on the planet is spending 4 minutes a file to open it. So basically, a lot of what we did as we started to think about that is, how do we build something that's familiar? So that means there are certain things about the interface that we can't change. So essentially, imagine building something with both of your hands tied behind your back. So we needed to fit within that constraint. So we started to look at what are all the different things that he does, and how do you understand the context of use and automate a lot of these actions under the hood, so that when he opens a file, he just opens a file. He doesn't have to think about this as a series of mouse interactions. And how do you do that in a way that's familiar and that looks like that interaction? But then over time, what we ended up doing is enabling him with his old system and his new system, and to switch back and forth, which actually then enabled us to understand what he's using his old system for and what he's coming to our system for, and over time just essentially make everything better. So this was essentially an 8-year process where he switched to our system in a couple of years, and then we just continued to iterate and improve it, and then we took it out to open source to ensure that other people with disability can use the system. But part of doing that is really trying to figure out, how do you scale a system like that to everyone? And one of the hardest things about assistive technology is that the economies of scale don't work. So, you can't assume that you can build the system that then millions of people will actually utilize. So then what we had to really do is, build a platform that can allow for innovation to happen on top of that platform, and enable, people to bring in all sorts of technologies, whether it's different sensing modalities or different word prediction systems or whatever it is, to actually improve that experience. So a lot of our focus on the open source system was to really lower that bar of innovation so that anybody can bring their piece of innovation without having to rebuild a whole system. And one of the areas that we continue the research, we're continuing the research in two directions. One is, I mentioned Stephen being able to actually move his cheek to push that button. In some sense, he's actually lucky because he still had that movement that he could utilize. There are a lot of people who actually are locked in and don't have a single muscle to move. So in this case, one of the things that we focused on is actually brain-computer interface and utilizing EEG to actually control the system. And a lot of the focus here is how do you actually reduce that barrier? Because today, if you want to use a brain-computer interface, you're talking about thousands and thousands of dollars to get gazillion electrodes to get the fidelity that you need. So the approach that we've taken was, can we actually reduce the need for high fidelity sensing and compensate for that with much more sophisticated, processing and machine learning to actually make it more usable? And can we actually reduce the attention that is needed by people to actually use that system? And that's some of the work that I'm showing here. And then the second path that we've been going down is, can we actually start to utilize human AI collaboration a bit more? So rather than just, in the case of Stephen, what he was comfortable with is using word prediction. But he didn't really want anything beyond that. He wanted to be able to control every letter of every word. Now, if you think about it, what we hear from many people with ALS is one of the hardest things for them is to maintain human connection. And this long pause, imagine somebody saying something to you, and then you start to type this thing, and even if you improve the typing and the prediction, there's still that long pause between the time that somebody said something to the time that the system starts to actually say something. So one of the areas that we're looking at is, well, can we actually utilize a lot of the AI technologies in terms of response generation? So if the system could actually listen to the conversation and understand what the person might be wanting to say, can we then make that interaction at a higher level? Can somebody now choose from a set of responses rather than have to put together every single letter or every single word together? So that's kind of the path that we're going in. How much time do I have? That's okay, so there's still Q&A after that. Okay, great. So I'm just trying to figure out what do I dig into? Okay, so one of the areas that we've been really, so as you talk about getting AI to scale in the real world, you really have to step back and say, how do we ensure that we're putting responsible technologies into the real world, right? And I'm sure you're all aware of all of the backlash that we've seen all over in terms of getting AI into the world. I mean, I remember 3-4 years ago when there was so much optimism and euphoria about what AI can do to help people. And frankly, over the last couple of years, every time I see an article, and this is in like everyday media, I'm not even talking about technical media, right? I'm talking about just everything that anyone looks at is all about how technology and how AI is actually hurting people, from bias to lack of safety to take your pick, right, on how, or violating privacy, or all of these different problems. And I think as AI researchers, we all really have the responsibility to think through, how do you build responsible systems from the get-go, right? We can't just simply assume that we can go ahead and hope for the best, and then somebody's going to figure that out. It's up to all of us to figure that out. And one of the things that is really needed for this is to actually have multidisciplinary collaboration and centers, like this one, for example. So one of the points I really want to stress is understanding uncertainty, right? So a lot of times, I mean, we know that I just spent whatever time I spent trying to convince you that these technologies are unreliable and we have to spend all of this effort and energy to make them more reliable by all of these different methods. But at the end of the day, that's the reality of AI systems, right? There are limitations to how correct they can be. So rather than assume that we're not going to be able to utilize it until we get these things to be at the 100% reliability, which will never happen, instead, we need to be smarter about how do we deploy these technologies into the real world and think about uncertainty of decisions and inferences as a key element into the design of the solution, right? So if a system not only can tell you what it thinks it's seeing, but how confident is it of that, then when you start to build these systems, right, as a whole system, you can actually take that as a first-class citizen and decide what you do when the system doesn't know or is uncertain about that decision. And, as I showed earlier, you can use it to figure out, how do you fuse different information together. But you could certainly use it in a human AI system to give the human a sense of that certainty, right? So that's really an extremely important thing. And some of the research that we're doing in this space, specifically on probabilistic computing, is trying to really identify where we're able to understand where these networks are actually trained with information that's quite different than what it's experiencing in the real world, right? And clearly deep networks are notorious for making decisions and being extremely overconfident about the decisions that it's making. So some of the work that we've been looking at in terms of out-of-distribution detection and trying to understand is the certainty that the network is actually giving is the network actually certain of the decision that it's giving, as opposed to here's the decision and here's the softback probability, and that's actually what we think is the accuracy, which isn't really a valid case, and this is what we're actually showing in this case, right? So in the case of a deep network, you're actually showing the data that is totally out of distribution, and it's actually reporting high level of confidence in that data, even though it's actually not correct at all. And if you start to utilize Bayesian deep learning, then actually you start to see the difference in the confidence based on whether it's actually in network or out of network. And this is really an area that at Intel we've been quite focused on, and not only with our own internal research, but actually funding an ISDC to look at probabilistic computing as an alternative way of actually bringing some of that innovation to try to actually solve some of the brittleness of deep learning, right? And how do you start to marry the best concepts of probabilistic computing and deep learning to actually improve the robustness of these systems? Okay, so how about I stop here? Let's just stop here and open it up for questions.
We have some time for questions from the audience.
Thank you for this wonderful speech. I'm Hong Juan Chu, College of Management, this university. I'm curious about the education. You mentioned that kind of a layout and also the monitoring system. But just recently in China, there's I think the primary school, they use this platform and layout, try to improve the kids' learning effectiveness. But he abolished in the end. So I would like to ask whether when you talk about that kind of technological assisted learning, whether there's a kind of condition when a government or even a university or a primary school would like to apply this approach to improve. Certainly I have this kind of a concern when I teach in the College of Management, and I still would like to see what kind of technology I can infuse with, for example, case-based study I am using for for teaching English teaching class for the whole university, also plus for students from overseas. So thank you for your comment.
I'm sorry, I'm just having a little bit of a hard time hearing well. So you're asking how can those be utilized without negative side effects? Well, that's a very good question. And part of the problem, and this is one of the things where I was trying to touch on the responsible AI part of the picture, right? When we're actually building systems, we're bringing really multidisciplinary people to look at what are the possible side effects of these systems. Who gets this information? Who is this information shared with, right? Who is empowered with this capability, right? So every time we're actually looking, so we've worked with different groups to try to figure out how would we take these technologies out, right, into the real world. And you can't really assume that you're going to build something and then just kind of anybody can take it and do whatever they want to do with it. Because really the side effects of this technology, specifically when you're talking about kids, right? Because kids end up being the ones that actually will probably bear the negative side effects of these technologies. So I would say that for me, the way to solve this problem is by bringing a multidisciplinary perspective into the problem. So when we bring the social scientists and the designers and the technologists together, the discussions that we're having, in fact, one of the things that we do is we have this kind of a review process, right? Where we have all sorts of questions that we ask of all different AI projects, right? What we're really trying to do is say, okay, what are the things that we have not thought about, right? Who are we empowering with this? What are the ways that we wouldn't have anticipated, these side effects to happen? And frankly, it's very hard for technologists only to make that happen. This is why you really need the social scientists in this equation, right? Because otherwise it's very hard to actually solve that. And as technologists, we try to solve the technology issues without necessarily understanding the ramifications. But thank you for the question. That's really something that keeps me up at night.
In your slide, you talk about the ground truth. And end of your talk, you say design with uncertainty in mind. I think evaluation is a very important part for machine learning. Under the ground truth, under the uncertainty, how to evaluate a good machine learning algorithm.
Yeah, I totally agree. And basically, my point is, the reason I mentioned specifically emotion recognition is that ground truth is very ambiguous, right? I mean, if I'm trying to train an activity recognition system, to a large extent, you can watch what somebody is doing and infer with good human ability, right? A very, accurate determination of the ground truth. When you get to emotion recognition, if you actually ask humans to figure that out, it's not that good, right? So my point is, all of this is true for all sorts of recognition problems, but I think emotion recognition is even harder because of the fact that ground truth is ambiguous. So across the board, it's actually quite ambiguous. I think the uncertainty point that I was trying to make is that rather than assume that you're going to have a system that's going to recognize something and then you're going to utilize that recognition to make a decision, you need to actually inform the system that you're building, not only with the thing that you've inferred, but how certain are you of that inference? Because then you could imagine doing something different. Like, we don't have to solve all the problems in the AI system. We can solve the problem from a design perspective. Again, if you bring designers into the equation, right? It's like, just think about a simple thing, right? I'm trying to make a decision whether, I'm automating a lot of analysis of images, trying to figure out, cancer detection. Right? If you understood what are the things that the machine is not good at detecting, you could actually filter these specific ones and forward those to a human to look at them, right? That's a way of actually incorporating the uncertainty of the recognition into a complete system design and not just thinking the AI is going to solve every problem on Earth, right? Which it's not going to.
So we need a period of time to evaluate your AI system. We cannot just use traditional machine learning algorithm, just a single shot, a test set, a validation set. It seems not enough to evaluate the uncertainty behavior.
Well, I mean, I would say you need the system to tell you what it knows about uncertainty. You also need to have humans in the loop to also validate that, right? Because it's like you can't also assume that the uncertainty detection is perfect, right? I mean, it's just, the whole point that I'm really trying to make is that when we think of human AI systems, we really need to think about how do we bring the best out of both of these. And you know, today I mean, everybody knows that diverse populations will come up with better decisions. I would argue that there is nothing more diverse than a human and an AI system. Like, let's just utilize the diversity in both of these systems to actually create better collaborative systems, rather than peg one against the other.
Thanks. Really nice talk.
Thank you.
So thank Lama for very
Okay.
so very nice talk. So my question is that when we design a new technology, so in the end the technology will evolve and meet the people in some middle point. Okay. So how can we be sure that when it's another new technology, how can we say that the human should approach the technology or technology will approach the human?
Can you say more about what you mean by approach?
Approach means that some the human may learn to let's say we learn to use the keyboard, right? To use the mouse, right? Or maybe, but on the other hand, we also want to make the technology adjust to human. Yeah.
So you're saying how can we meet in the middle somewhere?
Yep.
Well, yeah, that's a good question. I mean, okay, so I would say that what we have today is people adapting to technology, right? I mean, that just think about every interaction that we have with technology. There's nothing natural about the way that we interact with any technology, right? So we've actually trained ourselves, including the way sometimes that we speak, so that we can be understood by technology. Now, I would argue that I don't think that there's an answer to this question in the abstract. I think it's a question of evolution. So if something is usable enough and is needed enough, there's almost like those two vectors, right? There's the vector of usability and there's the vector of need. And you definitely, I mean, I saw a lot of that in the assistive computing and, you know, people with disability. That in some sense, people are willing to take on things that are really not that usable because they have a high need for that technology. So in some sense, it's a question of technology will get adopted if the need is at a level that is higher than, you know, the usability, like the system usability meets the need, right? Now, I would argue that as technologists, we should be striving for making technology totally disappear, right? Where you're not really thinking consciously about how you're actually interacting with technology. That is a lofty goal, and it's something that's going to take a long time. But I think, you know, trying to figure out in a lot of the interaction work, right? So some of the slides that I skipped around, you know, transparency of systems and trying to make systems, you know, people try to understand how systems are working so that you're actually enabling better human AI collaboration is a key point to where this technology needs to go forward, right? And there are subtle things that we could do. I mean, I'll just give an example. There is some really quite amazing work happening in Berkeley on robotics, right? And part of that work is about trying to, if you imagine a robot wanting to accomplish a task alongside a human, right? One way of thinking about this is having the robot do the thing in the most efficient way. However, if you assume that there's a human around, maybe the way that the robot should be accomplishing that task, including how do you get to grab something, should be cognizant of what the human will have as a perception of what this person is going after, what the robot is going after, right? So even in the actions that you take, How can you improve that transparency so that you're enabling the human to better interact with that system? And I think there is a lot of interesting research around transparency that gets us there beyond what we usually think about today, which is the system understanding the person when they're speaking and all of that. There are a lot of other things around that that are actually interesting.
Okay, I'm pretty interested in your multimodal fusion. For most of the research, you try to pursue the goal, and the goal is pretty definite. Isn't that true that when you try to pursue the multimodal fusion, the goal becomes so murky that you really have no big idea, okay, what is going on? So,
say more. Give me an example. I'm not sure I'm agreeing that the goal becomes murky if you bring in different modalities. Give me one example that you're thinking of.
Okay, because for the research you try to get one specific target, right? But if you try to know, okay, say you mentioned RFID, you get 1,000 of the RFID. It seems like you try to get as much information as possible from a different the aspect. But okay, I just feel curious, when you do that, what is the specific goal you want to pursue? Isn't that true that it just same as the one specific mode, not the multimodal that you try to fuse together?
Yeah, so I mean, okay, so let's take that example specifically, right? If you're thinking about a retail scenario, right? You have all of these tags, all of these objects in a store tagged with all of these tags. The point I was trying to make about the RFID thing is that when you have all of these tags, it's really very hard to understand the interaction because of the fact that there's shadowing effect that happens. So that's what I was really trying to get at. But now if you think about a multimodal system, think about vision and RFID, right? If what you're trying to figure out is, who's interacting with what objects, the RFID scenario is nice because it will tell you what object is being interacted with, and even with a camera, it's very hard to see maybe the specific object that somebody's interacting with, right? But the vision system can tell you much more about, the person who's interacting with this, and in some cases, tracking where this thing went as somebody takes this object and moves it around. So a lot of the analytics that you need to figure out in these settings will actually utilize multimodality, even if one specific detection is better suited to a specific modality. So that's really the point that I was trying to make. But on the RFID piece specifically, my point was that even though we can prove out systems and come up with algorithms that work in controlled environments, the minute you put them in the real world, everything starts to break down. And that opens up a whole set of other research opportunities to actually think about these algorithms differently. And what I'm trying to do is encourage people to look at that part of the problem, because there's a lot of research potential in that and not just an engineering effort. So that was really kind of the higher level point that I was trying to make. I think I'm out of time now.
We have 1 minute.
Okay.
Any last minute?
So a short question, or a short answer perhaps.
Okay. Nice to meet you, Lama. I just have a very specific question. Like during the engagement analysis for a student, I saw the pilot study, you have to label if the student is engaged or not. And I'm just kind of curious, how can you determine if student is engaged? Because it could be a very ambiguous or very big concept. And I'm just very curious about what metrics do you use to determine that?
That's a fantastic question. It's not an easy thing to do. So what we did is, not only did we look at, so we had multiple labelers looking at that data. Not only did they look at the camera data that's coming in, but they also looked at what the student was actually looking at on the screen, right? So they had access to all of this information as they labeled. Then we had different labelers, right, looking at that. And actually, so there's another paper that I can refer you to look at. We talked specifically about the labeling problem. But one of the things that we've also recognized in doing that, we've done a lot of studies to try to understand, is the labeler accuracy impacted by some of the cultural assumptions, right? So we've had people from different cultures try to label this data, and you could see a major difference in inter-rater agreements, right? Which is one method of trying to understand how easy is that labeling task, right? And we definitely saw a big difference when we actually tried to match the culture to the people who are being labeled. But yeah, we utilized that information and we looked at inter-rater agreement to improve the certainty in the labeling decision. But I can refer you to some of the papers that we published there as well. Sure.
Well, I hate to interrupt the very interesting discussions, but our time is up. So let's thank Lama again for the wonderful speech. So we have a fully packed schedule, so there is no break in between this talk and the second talk that will be delivered by Professor Xiaoyi Jian, and he is one of our very own from National Taiwan University. And so one of the reason that we are going to hear this particular talk is not only this is a very interesting topic on distributed intelligence at the very forefront of machine learning, combining the best technologies in both embedded systems and software, deep learning and so on. But also this technology is not just academic. Some of these solutions have been adopted by Intel and is incorporated into Intel solutions. So today, several of our talks, we are showcasing the results of our productive collaboration with Intel. And also, another part of the technology is incorporated into Compose product of hearing aid. Okay, so I'll let Professor Xiaoyi Jian take over. Okay, thank you.
Okay, so thank you for your introduction. In the next maybe 50 minutes, I'm going to present our achievement in the project, and the title of my talk is distributed intelligence. Distributed intelligence is basically a computation framework for IoT. Okay, and beyond this computation platform, we have two applications. The first one is the video object tracking. Okay, and the second application is speech noise reduction. Yeah, so basically these actually are two different applications. That means that we didn't do it in multi-model way, as Lama just mentioned. The two different topics. Okay, and the two PI of this project is myself, Xiaoyi Jian, and my colleague, Dr. Yu Cao from Academia Sinica. Okay, so my background is more about the double E and the electronic engineering, and my research is about the multimedia IC design. And for Dr. Cao, his research is about the speech signal processing, and his work with Academia Sinica. Okay, so here is an outline of my presentation. First, I will give you a very short introduction of our project. And then I think the major topic we want to discuss is where should the computing be located. Okay, and then I will show you some of the achievement. The first one is about the multi-camera tracking of the human object, and the second one is audio denoising in IoT. Okay, and both of them we will have a demonstration in the afternoon. So you're welcome to go to our demonstration site. And third part is what we call one of the key component for the IoT computation framework. Okay, so here we will show you one of the optimization methods for neural network. Okay, so then I will conclude my talk. Okay, so I think the audience here should be very familiar with IoT. Okay, and there are two key features in IoT. And these smart things are connected to the internet, and they are smart. That means that this device can analyze the data and generate some insight or some context. Okay. And there's another buzzword called AIoT, IoT is actually a combination of the IoT and AI. So we call it the Internet of AI things. Okay. So you can read this chart. In IoT, we have deployed a lot of sensors. And these sensors can retrieve a lot of information, a lot of data from the physical world. And this data, we call it ultra big data because these sensors will continuously capture the information from the physical world. Yeah, so we call it ultra big data because the size of data is very large. Okay. And when we transmit this kind of data to the AI computing platform, it can generate more information, more data, more insight for the environment, and then feedback those insights to the IoT and to make it even smarter. Yeah. So it will become a positive cycle. So you can see the AI, IoT, and big data are just the same thing in the whole system. Okay. So the problem is that where should computing be located? Okay. You can see from this chart. So assume these are the smart devices, are maybe the smart cameras. Okay. And these smart cameras are connected to the cloud through the aggregator. Okay. So where should the computing be located? From the internet, we call it the big data, but as I just mentioned, now we call it the ultra big data. Imagine this is all the smart cameras, and for all those cameras, they capture videos 24 hours, 365 days per year, yeah, continuously. So the data size is actually extremely large. Okay. So some people may say, oh, you just need to transmit all the data to the cloud, and the cloud can help you to handle all the analytic tasks. Yeah. However, it is actually not possible. Yeah, because when you transmit all the data, all the video data to the cloud, one of the problems is that the communication framework cannot handle it. It's too large. The bandwidth is too high. And the second problem is that it causes a larger burden for the cloud storage and the computing. It's not possible. Okay. So maybe the other approach is that we put the computing at the edge. Yeah. So is it true? Is it the right answer? Actually, no, because our consumer will buy this product, and they cannot afford a too high price. So you cannot embed the GPU in every camera. Actually, yeah. So this is actually another answer. So where should we put the computing? Okay. So in our point of view, the answer is distributed intelligence. Yeah. So distributed intelligence, that means you need to put the computation all the way from the sensor to the cloud. Okay, that's our point of view. So that means you will put the computation in sensor, in aggregator, in cloud. Yeah, and from the process from the sensor to the cloud, it can be viewed as a kind of a process to filter out the unnecessary data. It can also be viewed as a semantic level increase. Yeah, from the sensor to the cloud. Okay, so for example, when the sensor capture the video, yeah, it's just raw data, a lot of pixel values. Okay. And after computing on the sensors, we can increase the semantic level to a higher level, maybe the feature level or object level. Okay. So with a higher semantic level, the data size is actually smaller. And after the aggregator analyze this data from a lot of sensors, it can further transmit the higher level data to the cloud. Maybe just remove some non-important information. And finally, at the sensor and at the cloud servers, it can do the most high level analysis to generate the context. For example, these two people, these two humans are Paul and Peter, and the task they are working into the office. Okay. So how about the computing platform? We believe that at different node of the IoT network, there will be different computing engines. Yeah. For example, in the cloud servers, I think the answer is very obvious. Yeah, it must be the CPU, GPU, or FPGA, something like that. So I think Intel will play a very important role in the cloud server. We all believe that. Okay. However, for the edge part, including the aggregator and the sensor, I think there will be maybe several different kinds of computing platform. For the aggregator, we believe that there will be a kind of SoC and integrate with the neural processor inside the SoC to do the computation at aggregator. Okay, and in the sensor part, we believe that in the future we will embed some lightweight learning engine inside the sensor. Yeah, so so for this engine, it doesn't need to handle everything. You just need to handle a part of the computing task. Maybe just remove the unnecessary data and transmit the important information back to the aggregator and back to the cloud server. Okay, so I think that our focus is on at edge. Okay, in this project, we focus on at edge. So this is the structure of this project. So basically, we have two parts. The first part is the edge computing platform. So here we design the hardware architecture as well as the optimization framework for the neural network. Okay, and on above of this edge computing platform, we target at two different applications. The first one is the object tracking across camera network, and the second part is the audio processing at the edge. Okay, so I will give you three important representative work from each of them. Okay, so let's start from the first one, distributed multi-camera tracking. So let me show you what is the task of the multi-camera tracking. So in this example, there are 3 cameras, and for example, for this object 4, when he leaves this camera, and then we will check this person at the other camera, so he will appear here later. Yeah, here. Yeah, for the object 4. Okay, so this task is we want to check the object across different cameras. Okay, there's another key technology here we call the person identification, person re-ID. Yeah, so you can see after we find the human object from different camera views. Okay, so we want to know if this person and this person belong to the same person. Yeah, so the task to recognize if they are the same person is a person identification. It is actually a very hard task. Yeah, because you know that for these different cameras, we have different point of view for the person, different view angles, and different lighting conditions, and different camera settings. Yeah, so it's actually a very hard task. Okay. So with the replication, so this is a typical pipeline for the multi-camera tracking. In single camera, we first detect the human object, and then we link this object into the tracks. Okay, the human tracks. One track representing one human object. Okay, and then we consider the inter-camera relationship. So in the different camera, we will try to use a identification to identify if this person and this person is the same person. If they are the same person, we can link this track together. Yeah, so that we can finish the multi-camera tracking task. Okay. Okay. So I think back to the similar questions. So should we do it in the centralized approach or distributed approach? Yeah. Actually, most of the existing work in multi-camera tracking, they do it with a centralized approach. That means that they collect all the information to the server and then do the analysis at the server. Yeah, so it's a centralized approach. And as I just mentioned, it's actually not infeasible because it causes an ultra big data problem. Yeah, so we in this project, our target is to develop a distributed approach for multi-camera tracking. Okay. So let me show you the concept with this figure. So in this figure, all the sensors has a computing capability. Okay. So you not just capture the information, you can further analyze the information. So for example, when one subject go inside the camera network, so this sensor will find that there's a new person in this network. So it will assign an ID to this person. Okay, and later when this person leaves the camera view from this camera to this camera, yeah, like this one, and they will hand off the information, and then this sensor can also know, oh, it is a camera. This is the person A. Yeah, they share the same ID from their neighbor camera. Okay. Okay. So that's what we call the distributed way, because all the things are done at the sensor. Okay, and nothing was done on the cloud server. Okay. So similar idea, when there's another person here, maybe we can assign a different ID to this person. And there is other usage scenario. For example, when the cloud server want to talk to the all sensors to say, hey, oh, please send the information of the subject B to me. Yeah. And he will broadcast the information to all the sensors. And if this sensor have this kind of information, he will transmit the information back to the cloud server. Yeah, so it's a kind of interaction between the cloud and the sensor. And the sensor can actually do a lot of things at the sensor side, and the cloud can do higher level things and interact with the sensors. Okay. So how can we do that? So this is our proposed the method. Okay. So for each sensor, we have an ABC sensor in this example, and there are two edges here. This edge means when the people leave the camera A, there are some route go to the camera B and the camera C. Okay, and then we also maintain a special temporal model between the cameras. Okay, and for each sensors, it will maintain a database. Okay, so we call it in the database in the buffer. The database is record some information for the person in this camera network. Okay, only a part of the information. Okay. So when one of the person leave the camera A, okay, the related information will pass to the neighbor camera. For example, the camera B and the C will have the related information from camera A. Okay, and then if the camera C found that there are a new person inside his view, it will first check with the traveling time model. Yeah, so that means that we have maintain a model to know from camera A to camera C how long will it takes. Okay, if this object appear in the reasonable time, maybe these two persons are possible candidate. Okay, and then we will use the re-identification algorithm to find the real match between the input data and the database, and then we know the ID. Okay, we can assign ID to the person. Okay, so this kind of approach is actually online. Yeah, so it just finish all the tasks in the real time, and it's distributed way, so you can know all the tasks. It doesn't involve with the central server. Okay, all the things can be done at the sensor side. Okay, and very suitable for IoT applications. Okay. Okay, and how about the performance? I think the major concept of this kind of approach is that since we now have a very powerful re-identification powered by the deep neural network. Yeah. So with a very powerful re-identification, maybe we can skip the central server. We just do everything at the sensor side. Yeah. So I think this chart gives you some example here. Okay. So there are three columns. The first column is called the re-identification performance task in metrics, and second column is about the inter-camera tracking performance, and the third column is about the performance of the whole system. So you just focus on the third column. Okay. So the first Duke and TMC is a kind of a centralized approach. Yeah, it's a centralized approach. So the performance here, the numbers are the higher the better. Okay. And we have three versions: 2016, 17, and 18. This one is actually based on the deep neural network. Yeah, and the performance is actually not very good here. Okay. And in our 2017 and 2018 version, you can see the performance become better, even better than the centralized approach. Yeah. Okay, so I think the key learning is that with a powerful identification, it is possible to put the computation at the sensor side and also achieve a similar performance to the centralized approach. Okay. And we also done a lot of evaluation of a different identification method from different. These four different neural network for re-identification, and this one is a handcraft feature. Okay. For the left chart, the horizontal axis is the inference time. The vertical axis is the mean average precision. Yeah. Okay, so you can see the very interesting part is actually for the handcraft features. The performance is not good. Yeah, it costs a lot of computing time. Yeah, it's maybe different from what you thought. Yeah, that's it because nowadays our framework, our GPU are optimized for CNN. So for this non-CNN task, sometimes the required computation time is even longer than the CNN-based approach. Yeah. So you can see among these 4 different networks, the one performed the best is the ResNet. Okay, and the one who can give the lowest inference time is maybe the SqueezeNet. Okay, and in the right hand side, we show you the computing resource requirement, GPU time, and the memory requirement. So you can see the one with the highest accuracy costs a lot of computation resource, which is the ResNet. Okay, and the SqueezeNet is actually a very good solution because it can use a very reasonable computing resource and also achieve a nice performance. Okay. Okay. So our suggestion is that for a lightweight CNN model, you can choose a SqueezeNet, and for accurate CNN requirement, you can choose the ResNet. Okay. So the learning instead, I think, it depends on the platform. If you have a very powerful sensor computing platform, you can choose the ResNet. And if your sensor computing platform is not so high, you can choose the SqueezeNet. Yeah, I think it depends on the configuration of the platform. Okay. Okay. So here I give you the result of the multi-camera checking. Okay. So actually, the result is not easy to view. You should pay attention here. So maybe you can start from this person. He is checked by a blue box here, and when he leaves this camera view, I believe she will appear here. Wait a minute. Okay, so here. Okay, it's the right one. Yeah, maybe. Yeah, the blue rectangle here. Yeah, maybe the screen is we need a very high resolution. Maybe you can start track from this one. This girl is checked by the light blue box here. Okay. And now I believe he will enter this view. She will enter this view. Here. So you can see we maintain with the same ID with the light blue box here, and then later I think he will go to another view. Wait for a second. Remember, is here is a light blue bounding box. Yeah, so we check this object across a different camera very successfully. Okay, and I believe she will enter this view later. No. Here. Yeah, so you can see still the same bounding box. We can check this object. Yeah, so you can see we can successfully check the object across different cameras in the camera network. Yeah, so it's actually very difficult to view from this larger lecture hall. Yeah, so we also show you the other way. Yeah, so for example, we can focus on one single object. This one, this person. Okay, so we just give you all the video capture this person together as a video summarization. Yeah, so yeah, this is the person in our focus. Yeah, the person here. The person here. Here. Yeah, so you can imagine there's a lot of complication with these technologies. Okay, for example, when you deploy the 100 camera in the airport, and then you can check every passengers inside the airport. You can know where he's going and his behavior, okay, and his real-time position. Okay. And we will give you a real-time demonstration in this afternoon with an Intel platform. Yeah, so we use the Intel NUC. It's a very powerful computing box. Yeah, very powerful, like a PC. Yeah, we use this platform to show this real-time system. And this revocation and tracking system is also implemented in the Intel ISTC Visual Cloud systems. Yeah, so this is actually an open source project. So if you want, you can also access all the information from the Visual Cloud system. Yeah. And we also have a task, and we call it unsupervised re-identification. Yeah, because we believe that the supervised re-identification is actually unrealistic in real practice. Yeah, that means in the real practice, you usually don't have the label data in the when you deploy the cameras. Yeah, so I show you the problem here. Yeah, so when we train the market and the Duke are different famous re-identification dataset into this field. When we train the network in the market dataset, you can achieve a nice rank 1 accuracy, 65%. But when you deploy the same network to the other domain, the Duke dataset, you can see there's a large gap of the performance. The performance will reduce from 65 to the 23. Yeah, because this is the new domain. Yeah. So if some people will say, oh, you need to use more data set for training. So the second approach is that when we put more data set for training, okay, more data set but not exclude the Duke data set. Oh, you can see the performance will become better to 72. But the performance on other domain is actually unpredictable. Yeah, because this is a new domain for this neural network. So this is a domain transfer problem in neural network. So some people start to do some unsupervised learning approach. Yeah, so this is other work, not ours. So they can perform like this one, 61%, yeah, which is very nice. Yeah, and how about ours? Our performance is this one. Yeah, we have a new approach. We can achieve 85 minutes, but just finish the first test. Okay, 85%. Okay, so you may have a question that why this one can beat the unsupervised, the performance on unsupervised. Yeah, because in our engine we also included the spatial temporal information between the cameras. Yeah, so the performance will become better. Yeah, so if we also include the spatial temporal information into this supervised one, okay, the performance will become higher. Yeah, but our unsupervised approach can approach to the supervised approach. Yeah, so that's a key message I want to show you. So because of the limitation of time, maybe I will skip the third part. I only focus on the second. The audio denoising in IoT. Yeah, so this is the second part. Okay. So when we do the speech communication, there are two scenarios. The first one is a person-to-person, human-to-human communication. The second one is a human-to-machine communication. Yeah. And imagine there are maybe some noise. Okay, in the usual situations, there are some noise in the audio. Yeah. So when we do the human-to-human, it will cause the lower speech quality and lower intelligibility. That means the human the other person cannot understand what you are talking about. Yeah, and we will increase the listening effort for the listening. Yeah, and when we do it for the human to machine communication with a voice, yeah, the noise will cause the lower recognition accuracy for the automatically speech recognition. Yeah. And it will also lower the quality and the intelligibility of the text-to-speech task. Yeah. So we will propose an audio denoising engine inside the edge part. Yeah. And we believe that we should finish the noise reduction at edge and then we can increase the performance of the automatic speech recognition at the cloud. Okay. And there are two ways to do the denoising with the deep neural network. The first one is a direct mapping. That means that we use some training data with a clear voice and the noisy voice, and then we can train the neural network here. Okay, and then we can use this neural network to direct denoise the input audio to the output one. Okay, so this is a direct approach. And the second one is a masking approach. That means that we use the DN model to generate a racial mask, and then we use this racial mask to reduce the noise with element-wise multiplier. Yeah. So from our experience, we found that the racial test can perform well, perform better than the direct method. Yeah. So that we use 3 metrics here. This metric is used to evaluate the audio quality, and this one is to measure the intelligibility. That means how the machine can understand what you are talking about. Yeah. And this one is about the distortion. So for this two, is higher the better, and for this one, the lower the better, because this is a distortion matrix. Okay. So after that, we integrate it with in the smart speaker. Yeah. And the backbone, we use 2 backbone. The first one is Google ASR, Google Speech Recognition, and the second one is Amazon Speech Recognition. Okay. So the metric we use is the error rate for the word recognition. So the number is the lower the better, because this is the error rate. Okay. So you can see in the noise input, the error rate is like this one and this one. Okay. And after we apply our noise reduction approach in Amazon platform, we can reduce the error rate from 62 to 28. So you can see there's a large performance improvement. Yeah. Okay. The improvement rate is 54%. Okay. However, this is very interesting is that if we apply this same technique at the Google platform, the performance actually become worse. Yeah, very interesting. We guess that because maybe the Google platform, they also embedded some noise reduction engine inside their audio processing engine, and there are maybe some interference between our approach and their approach, so it cause a worse situation. It's very interesting. And we will also integrate this technology to assistive listening devices. Yeah, so that means that we can use a smartphone to capture the environment speech, and then we can, after the process by the smartphone, we can use the ear set to hear the clear sound. Okay, so if you feel interested, we will also demonstrate this system in this afternoon. Yeah, so please go to our demo site to experience these technologies. Okay, so we also integrate this technology with Compel. So I'll show you some news. Yeah, so we cooperation with Compel. They have integrated with the AI ear set serial of the product, and they also integrated this audio denoising into their smart speaker product. Okay, so I think I will skip the third one and direct to the conclusion. Oh, there's other one. Maybe I'll skip this one. Okay, do the conclusion. Okay, so in this talk, I will show you several of our part of our achievement. The first one is the concept of the distributed intelligence. We believe it is a new computing or key computing framework in IoT. And second type I'll show you is the distributed multi-camera tracking. So with a powerful person identification, we can do it in distributed way, and the performance is similar or higher, even higher than the conventional centralized approach. And the third conclusion is that we use with the masking method actually perform better than the direct method for audio denoising, and it can help to increase the spatial recognition performance of the smart speakers. Yeah, on the Amazon ASR system. Okay. And the final thing we want to highlight is the industry impact, because I think in our project we have a lot of interaction with the industry. So we have a deep collaboration with Intel. Our system is actually integrated into the visual cloud system of the Intel open source, and we also will have a real-time demonstration on Intel platform this afternoon. And with Compare Electronics, we have integrated our technology into their assisted listening devices and smart speakers. And we also have a joint develop with Delta Electronics, but this one is included in my skip part. If you feel interested, we can talk about later. Okay, so that's all of my talk. Thank you.
So we still have a few minutes for maybe 1 or 2 questions. Oh.
Okay. Thanks, Professor Jen. My name is Richard. I'm from Intel IoTG. So one question about the distribution model, because right now I think a lot of, not only Taiwan but other, telco company or manufacturing company, they are building a hybrid model, like having the deep learning analysis to happen when the data is transit on the way to the cloud. So some compute can happen at the edge, some compute can happen in the 5G substation, some compute can happen in the cloud. How do you see that trend coming? Another thing is, I'm very interested about how the distributed re-identification model can beat the centralized model, because we can also associate the camera stream, the geographical relationship between camera in the cloud. Are we able to achieve the same thing in a centralized way? Thank you.
Okay. Thank you. Thank you for your 2 very good questions. And I think the first one is that we actually proposed the idea 4 years ago. So nowadays we saw that many systems they implement the same idea. So what you just mentioned is the same as concept of the distributed intelligence. That means we believe the AI, the deep learning computing, will appear every part of the network: sensor, device, aggregator, gateway, and to the cloud. So we believe that we can distribute the computing in different parts of the network to achieve the best performance. So I think what you mentioned is actually on the same direction of our approach. And for the second question you mentioned is the centralized approach and the distributed approach. So I think maybe the experience data I show you is maybe a little misleading. I think that the centralized approach should perform better than the distributed approach. And the data I just show you, that because a centralized approach we demonstrate there is an old approach. It's not based on the neural network. So the performance actually, even if it's centralized, is worse than our distributed neural network based approach. But if you put nowadays the most advanced neural network based in the centralized approach, I think it still perform better than the distributed one. But I think the problem is that it's actually not feasible, because you cannot put every data to the cloud server to finish the computation. It is not feasible. So we think the real practice, we should have some of a hierarchy. Some camera should be handled in local and finish the computation and transmit the process data to the next stage.
So one follow-up question is, when you having the camera to exchange the information, while handing over that identified object from one to another, are you following any protocol, any standard way to do that, or that is proprietary?
That's proprietary. Because I think we don't know there's other protocol here, but if you can share some of your view, as very welcome. So we just transmitted the feature information to the other cameras, so the data size is not large. But we don't know if there are some standard here. Thank you. Other questions?
Thank you, Doctor. I just have one question that do you have any calculation that the camera, how many computing power, like how many taps, and in the aggregator, how many taps? So you design your system. That is the first question. And secondly, is, according to that, then there are a lot of like NPU, VPU, GPU. So how you going to choose? I mean, in the camera, in the aggregator, how you choose such kind of chips or GPU? Thank you.
Yeah, thank you for your question. It's very practical question. Yeah, but I didn't have a real answer now because I didn't remember the number. But I think in my point of view, I want to make it very flexible. That means if the sensor computing power is not so large, we can replace with a simpler model. Yeah, and with a higher performance sensor, we can put a more complex model inside the sensor. Yeah, actually, we believe that the sensor aggregator, they can cover to each other. If the sensor is not so powerful, the aggregator can do more things. Yeah, so they should cover to each other. Yeah, so actually, in 2015, we also have another lighter version. We only use the Raspberry Pi and do the similar task. Yeah, so that's a kind of example. Yeah, thank you.
So I think we are running out of time, so thank you for attending this session. We do have some refreshments outside, and we'll come back here in 10. 11 sharp. Okay, thank you. Matthias 的档案是在这里还是？所以先把它校对，等一下就 switch 过去。对。没有在这里，还是这里。哦，好，所以那你来弄，因为我刚刚这里是有一个，就是我有做，其实我每一个 talk 就是这 invited talk 我都。对呀、没有，就因为这样子。我把它用同步语。对对对，好。
道了吗？好好，谢谢。赶快去找婉玲哦。什么？哦，好好，谢谢。
那这个给你。
好好，你放那个桌上就是好了，谢谢。你要几颗？全部。Dear Professor Matthias, dear Professor Max, yeah, would you like to test your presentation first?
I think it will try. It will work.
Okay.
I think it will work. Yeah.
Is it?
I have a question. How dark can we make this room?
Oh, dark, maybe like 150 at least. So we would try like it's up to 160. About like that.
160. What does that mean? What I mean is, can we switch off all the lights in this room? Is that possible?
Oh, you would like to turn off all the lights?
Yes. Is that possible?
We can try to do that.
For a short moment, in the middle of the presentation. But if it's very difficult, then I will skip that part.
So which page would you like us to take?
I think it's around 20, 25.
25?
No, it's okay. It's okay.
On the last one.
No, this is not my presentation. So, yeah. No, just yeah. So it would be slide 15 to switch. But if it's a big problem, then we can do something else. Where's the other slide?
Yes, the stage light.
Yeah. Stage light is fine. Stage light is fine, but the hall light, the rest of the room, is it possible to dim down, or is it difficult?
I'll try to do that. I'm not sure. I think there is.
Yeah. Okay, then don't do it. Then
Is there anything you want to say or not to say about it?
Oh, there are secret ones.
Oh, I want to know.
So I guess that we will see it.
Yes, we do. Yeah, pretty much on Yes, we have two extra microphones. So you can have one, yeah, and you have one where they run to whoever asks questions. 电脑老师还要电脑卷。
那我放这里。
It's okay. 现在我们开的是有玩
Test.
And in this is KJ, we didn't communicate properly, so I didn't realize that we just arrived this morning.
We have perfect communication, but there's always misunderstanding. Don't blame on the communication technology.
Oh, yeah.
It's a human issue, not the technology issue.
Okay, so do you need coffee or anything? Okay, so water for you. Okay.
But I have a slide as well, so I will explain some things so you can.
Oh, so you have the self-introduction.
Yes.
Oh, okay.
Yes, it's my second slide.
And you know, Matthias is promoted to
Associate.
Associate.
Yeah, thank you.
So do you have a habilitation system?
What? Habilitation? No, we don't have that. But the step from assistant to associate is pretty big, so that it sounds like that. Yeah. And then.
So you kind of have two steps, like your tenure.
Yeah. Actually, it's all different. So promotion is different than tenure, and sometimes they do together, sometimes in the sequence. That's different.
Oh, so even the sequence can be different. More complicated.
Yeah, they try to make it more individual and more complicated. would say 1 more week.
Are you staying for 2 more days? But you are going to be in Kaohsiung completely? And when are you leaving?
I'm leaving Saturday, next Saturday. But I will use the week to meet with people here and also to document all the stuff for Intel, because they want to collect all the code and all the things in a repository. So all the projects that we submit.
You didn't get a message? Stranded. Yes. Yeah.
Oh, it's good that we talk.
Send the note to everyone. All the people said same as moving forward. So I'll send you a message because they want all the projects to sign up on the account of the email service and upload them. I know. So you kind of get package already. So that's why it's not as easy to pick the whole new take some work. So similar with either there is some prior art, and something that you are doing on your own.
But it's sort of in between GitHub and package your directory, right? It's somewhere in between.
Yeah. So there is money.
Some of the part now.
Okay, so the thing with Intel is that initially they are trying to push for, because Xiaomi work is considered technology transfer is done, but they want to put a more than one. But after some effort, nothing really happened. Okay, so this is why they want to transfer. They maybe transfer everything. And if, at some point, you might be able to.
Wait.
So, package may be used for or may not be, depending on if there is any increase coming down the road. Okay. But I think they just want to have more organized repository of everything.
It sounds like bad experiences in the past. That they got all that and then stop it with that.
So this is kind of a way to convince the vendors to allocate additional funding and push it.
Do we have a fail that we can move?
你自己跟他negotiate, I don't care.
你是下一个吗？
我是下一个。
不是有，
下一个是下一个。
对，我说这 after this one is this. Yeah.
时候可以用直接对，在算他的。
他的电脑要连到我这边。
他连到你这里。
对，用那个 NtuEE70th。
你开了吗？
开了。
来吧。
好。
那炸了吗？哎，他已经开了。哎，不见了。那就开，没关系。
那我的直接用 Google Doc 的话，没有办法，只要我 share 给你，还是这怎么样？这个怎么 share 这样子？
再自信给我。
share 到你的名字吗？
对。
是你自己的名字，这个电脑是你自己的名字。
我现在不懂，老师你是要 email 给我，还是用 NtuEE70th？
没有，我是说我直接是 Google Doc 就直接用 Google 说上去。我中午再说好。
你现在是接 NtuEE 吗？
Do you want to? Okay.
如果不行，就让我插。
好。
不然怎么办？那你有那个？
不是 Type C 的。
插不会有问题。
对，插应该不会有问题。
但是他们想要比较保险。
我也是觉得插应该不会有问题。Yeah. 可以，应该是可以。Yeah.
好，那就这样吧。这样才可以录了。
我们现在录影。
好。
你会找我吗？
你就把它的放上去吧，先把它 post 出来，直接发的。
等一下，快到我电脑。
Okay, good morning again. Welcome again to the IOX the meeting. So this for this session we have two talks. The first talk is going to be by Professor Matthias Funk from the Eindhoven University of Technology, and he has been working with the center for several years. He is researcher. His research area is system design, design tools, and user programming. And today, with all the good intention, he's going to talk about this intentional programming, which is the title is From Design Tools for Systems to Interactive Intentional Programming, and that is something. Yeah, Matthias. Okay, you have a clicker here. This is just forward, right? Okay. Hello, good morning. Thank you for being here. Thank you for the kind introduction. I would also like to thank Lama for the great talk, because it gives me sort of a platform to speak about a certain kind of area of things that I'm researching. And maybe to quickly introduce myself, I'm sort of a person who stands between two different areas. So I'm a computer scientist. I did my PhD in electrical engineering, but now I'm in industrial design. So I'm interacting with designers on a daily basis. I do design research. I help designers do design research, and that is really, really interesting. And that is really a super important area as well, because if you think about liberating technology, there was a talk just at the beginning of today. Liberating technology means that technology goes into the world. And I think the word choice is really sensible. It's not unleashing technology. It's not like, here, technology, and then you drop it, and then something happens. There she is, yeah. It is about creating a pathway from the inventors of technology into the world of the users. And the world of the users is what we design for. So on this side you see 150-year-old science fiction That is the smart home that people thought about, okay, how cool would it be to have all these pulleys and all these wires and the cat feeding itself with milk, etc., etc. That's what people wanted. If you think about the now, if you think about the smart home, we have that. These wires are now wireless, but they are there. And there are plenty of more of these wires. Yeah, so this is actually very, very much looking forward and anticipating what technology might bring to us. But at the same time, we see a picture that is weird in the sense that technology is taking over the everyday. And that is what we see today as well. And we've heard it before, that people really have to do things differently because of technology. And that is a trigger for design to change that. So when we talk about design, we talk about the future every day. So this is the 95% or 98% of the time that we are existing and living and enjoying our lifetime. And it's not the weddings or the spring breaks and so on, but it's really the boring, mundane time. And we want to design for that. The systems of smart things is basically a sub-area of that, and we're talking about multiple products. Products or designs that exist on top of a collection or constellation of different products. All right. So I'm going to show you two designs here that are just representative of the many hundred designs our students and staff create per year. And the first one is a wake-up lamp that is part of a system of other objects in a smart home context. And it sort of shares data, it sort of tries to understand what's going on, tries to adapt to the user, and does a very good job. The second project is a home camera that is privacy aware. A home camera that basically does this peekaboo when it should not watch. So it will take photos about the context. It will be very invasive, but it will try to respect the user. It will not take pictures of people who are present. So this is an ongoing research project currently. And all these projects have something in common. They are connected, they use data, and they are in some way intelligent. And if we talk about designing new products, then our discipline has changed a lot. So it's not about the chairs, the cars, the shoes, the shirts, and so on anymore, but it's about interactive, connected products. And there are some contemporary challenges there. It's about that design really is more and more involved with technical matter. Designers need to understand technology, they need to be able to deal with technology, and it's really tricky. There are different approaches to do this, and we are really about bringing emergent technologies into the future every day. And what is interesting is that in many processes, you see that technology takes a certain time to create, and then quite often design happens for a short moment just to take the edges off, almost as an afterthought, and then there's a usage phase. And what we want to do, what my mission is, essentially working in industrial design department as a tool builder, is to increase the time that design can take to bring products into the world. That is really, really important. Yeah? So, and that might mean that we have to shorten the time that designers can interact with technology to make that faster. So designers are not just, well, they don't need to just talk about technology and connectivity, but it's also more and more about data. So there are approaches like data-enabled design, where we really have to think about how do we use contextual data in our design? How do we create loops that an intervention in the context can actually bring about change in the data we collect, and we analyze that, and so on and so on. So focus on data and connectivity. This circle is what you have seen in the talk just before. He used a different visualization, but it's essentially the same thing. So it's connectivity leading to data, leading to intelligence, trying to form a loop here. And I'm going to show you 3 different platforms that we built for designers that allow them to do this faster and better. So this is the mapping 1-to-1. You saw that correctly. we have a connectivity platform here, we have a data platform there, and we have some sort of intelligence platform, moderate, but something. So let's start with the first one. This one is a connectivity toolkit called NtuEE70th. It's a connectivity framework that is now being built since 2013, and it has been used by thousands of designers in the past. And what it does is basically, it's multi-protocol, it's multi-paradigm, it's really trying to give designers very, very simple tools so they can start making products or prototypes that send data, that share data, that communicate data. And if you think about that, it's very simple. It's not rocket science, but someone had to do that. So not every single student spends 6 weeks of a 12-week project trying to figure out how to set up an HTTP server. As simple as that, yeah? So our students are often reinventing the wheels, and they shouldn't do that. They should spend the time on designing. They should ask the questions of, why do we need this? Why do we need this technology? How do we mediate this technology in the life? And not how do we send a package from A to B and get some better package back? That's not the point. So we built something. And because designers are very visual people, we didn't just have to build some server technology, we also had to build visualizations, like this one. We call this the data canvas. And it basically allows the designers to collaboratively design different products in the same space. This is a floor plan, basically. And we just visualize what is happening, different channels, different messages, different events going on and out. And this is a really helpful tool for them to understand that something is happening, what is happening, how to debug that, and how to communicate what they are sending, what they are receiving, what they need to others and in between. Yeah? So it's a very important thing that we cannot just do stuff, but we can also talk about that stuff. Again, it is important to realize that it's not the single product that we want to design. It's a graph of designs. Yeah? It's a multiple. And on top of that multiple, we want to design experiences, qualities, properties, and so on. That is the new material. And so these emergent things, that's what we're interested in. This platform doesn't exist in a vacuum. You could have imagined, well, connectivity is something that has been done before. Yes, that's correct. So there is a lot of stuff out there. Now, why do we still make something different? Well, the emphasis on different, because many of these technologies are made for a particular purpose. It could be an application area. It could be a protocol, it could be a certain type of research, or, and that's what you see at the bottom a lot, it's a certain type of business interest. And they are not automatically, naturally aligned with what we need in design. Yeah? So many of these technologies have been used by people in our department, but they haven't been used very successfully, because there are hurdles, there is friction in aligning technology with certain needs. So, if you want to do this, we can do this really quick. Scan this, go to the website and see what happens. The room is pretty light, so I will explain what is happening. So when you scan this QR code on your mobile phone, most modern mobile phones will give you a little thing, and you click on it, you go to a website, and then you end up with a black screen that starts flashing. Now, if we were in a very dark room, and I have done that before for a similar audience, then you see that these flashes are all over the place. But at some point, after about a minute, these flashes start to synchronize. So at some point you see that the entire audience is flashing in a 1 or 2 second period. This is just an example of a very, very, very simple system that you can build on top of our platform. So basically what happens, you scan the QR code, you go to the website, the website connects via WebSockets to our platform, to all you others, and they agree, you can look in the source code if you want, they agree on these flashes. And they use a Firefly algorithm, so like a natural biomimicry algorithm, to synchronize, and that's the whole thing. If you shake your phone, then you get a different color. Yeah, oh, that's great reaction. Okay, I will continue. And you can continue shaking if you want. So this simple synchronization is something that is actually already a little bit higher up. So what we try to achieve is that prototypes can communicate. Great, check. They can exchange data. They can just talk about variables or data or just pieces of data, but not messages anymore. So we can abstract away. We can do shared state, we can do shared state machines, we can do synchronization, we can do coordination. So we can establish a total order on all these devices. So I had a pre-made version that would actually play a melody, but then iOS devices couldn't play sound properly, so I skipped that. So you only have the flashes and the color shaking. But these kind of things we want to build for designers so they can use these things. And they don't need to think about all these levels below, because it's just distracting. So what is really important is that they can share data, and not how. They just share data. The data arrives, the data goes away, fine. They can work with awareness. They see, oh, there's some other people in this room. Maybe we can do something together, or maybe we can design something that shares information about these people. We can talk about services and composition. We can talk about microservices, no problem. We can teach that as well, but at a very high level. I talked about these systems primitives, so you can just say, oh, well, use synchronization, use negotiation, and that's it. Yeah, you can build your small blockchain if you really want that, but that is the level that we're talking about. And finally, we really need to build integrated tools. Without these tools for animation, for visualization, for even scripting the whole thing in a domain-specific language and generating code for all the platforms, we've done that as well, that really brings about the change. I will come back to that later. Okay, let's talk about data. So data is the second point. In design, we see more and more that data collection is key. Llama has mentioned that today, that they need to get their hands dirty. They need to collect their own data sets. They need to curate data for the purpose of solving a problem, designing something. Yeah? So we need to create something there as well. And we built this. This is currently in the beta phase now, and we're serving about 800 people with this infrastructure. That's students, bachelor level, after the first year, like, oh my God, I need to design with data. How do I do that? Okay. Up to researchers that also sometimes don't know really how to do that. So this is really important. This is really important, how to educate people to get there. And also how to enable the data collection from a lot of different sources. So it's not just about collecting data, it's about organizing, structuring it, making it available for use. The end user counts, and that's, in this case, a researcher. So there is a lot of thought that went into this platform, and we built that with a team. And it is built actually on this connectivity infrastructure. So once your devices are connected, it takes you 2 more lines of code to send all the data into a database. Then you can analyze it. You can even feed it back into the infrastructure. You can feed it to a cloud service and run it back into a small embedded device and then do something. So this is really an enabling technology for our designers. Okay, what we want to do with that is we want to enable 800 plus people. We want to also ensure data integrity, but also scientific integrity. Students, they might cut corners. We don't want that. So all the data is there. It cannot be deleted anymore. We want to enable sharing and reuse. We want to really make sure that we get a network effect going. And the more people are on the platform, the better you can do stuff. The more data sets are there, the better we can do eventually machine learning. So all these kind of things go hand in hand. Last project, and this is actually the project that I did with a few others on the IOX Center. IIP, Interactive Intentional Programming. And on that side you see trigger action rules, trigger action programming, very simple stuff. Connecting sensing to some sort of actuation via a rule. And that's an if statement, conditional. If this is on, then that happens, etc. We found that is not super well aligned with how humans think. And well, you can think, oh, how do humans think and that? But actually the idea was, let's look behind. What is the daily practice? What is the practice of people in the home? Do they actually want to think about smart technology? Do they want to think about automation? Well, sometimes. Sometimes these people are aficionados. They sit in the basement and solder away. I don't know. But many of these people are just users, and many of these people, they're just living in that environment. They don't want to interact with that technology. They don't want to interact with the programming environment to make their lights go on and off. That's ridiculous. So we need to anticipate that these people have a right to using this kind of technology as well. So we thought about maybe we need to separate the interaction with this technology into long-term thinking, like, oh, I want to save energy, I want to be comfortable, I want to be safe, etc., etc. Intentions. And then ad hoc changes, like, oh, I'm feeling a bit cold, actually, right now, yeah? So I want to turn on the heating, or I want to have a different air or different lighting. So all these ingredients went into this platform. And there are a couple of questions, actually. So this is actually a very fragile system, and it fails quite often for a lot of people. So our intention was here to build something that is modeling what humans might want in a better way. Our other intention was that we want to allow people to interact with this system at many different levels. So we built a domain-specific language that gives you all the details. All the concepts are there. You can really manipulate the ass out of it. But there is also a UI for designers. There is also a mobile UI, and there's also peripheral UI. And I have to reference the demo here. So visit the demo, Yaliang's demo, later on. IIP is behind that demo. Yeah? So different interfaces interacting with a core system. And these interfaces give you different views and different capabilities to interact. So the peripheral UI at the top, that is very, very subtle. It's really in the background. It's really not something where you point and click and do stuff. But maybe this is exactly what we need for 80 or 90% of all users. Then the mobile UI is for people who want a little bit more control, and other UIs are there for even more control. So this is a nice exploration that we try to do here to interact with a smart interactive system that gives you different levels of expressivity. And for that we had to rethink what sensors are in such a system and what actuators are in this system. We had to abstract some things away. And we say, okay, there is a whole technology stack behind sensing. We can do a lot of things. We've seen a lot of things yesterday and today already. But maybe we make them pluggable. So we just hook them into the system once it's mature, once it's ready. And same for the actuation. So we don't really touch that we tell a lamp to go on, we tell a lamp to go off. But we simply say, okay, we give certain information to a room and all the actuators in the room, and they can figure it out. That's also an application of edge intelligence, that they figure out what 80% lighting means. Is it that the ceiling goes on, or is it that the table lights go on, or is it that they agree on something else, or the blinds go up because it's daylight? They figure it out. Now that's really about designing with the right abstractions. That's really trying to understand, to rethink, to ask, why do we do this? And then to find better abstractions and design for those. The system itself, this is a recent visualization of how it sort of communicates, but it opens up a lot of different new research questions that will take us hopefully from 2019 to 2020 to 2021 and do a lot of interesting research on intelligence. So for instance, how to make this whole thing explainable. Well, luckily the concepts are already humanized, so we can explain certain things like preferences very easily. What does it mean that we balance between control and delegation? Well, that's a super interesting design question, and that requires a lot of different new interfaces. What does it mean that we talk about execution semantics and actuator control in different ways? What does it mean to talk about different forms of smarter or richer information in the actuation layer? So there's a lot of stuff that we still need to do. And how does it all come together? So the interesting thing is, well, you maybe figured that already, that all these things are connected. So if we have this core of IIP, it interacts with sensors, with interfaces, with actuators via connectivity infrastructure. And we have that. That's great. That also means that once everything is connected, all our students can design new interfaces, can design new ways to interact with the lamps and all kinds of other appliances via that infrastructure. They just hook it in. They learn that in the second semester. No problem. So it's really putting things together. For the data, this is another important point. Whatever data goes into IIP or comes out of IIP, we store it. But using the infrastructure, we can also simulate stuff. We can schedule stuff. And that's great for designing. Because imagine I want to design a new light control. But for that, I want to simulate the day in the life of Bob and Mary. Well, then I can do that. I can walk into rooms. I can wave at all kinds of IR things. But I can also press a button and say, well, just play it. I've recorded it yesterday or 2 weeks ago. Just play it back and see how everything works. And then you stop and say, well, that lamp should go on now, or the light is too bright. And then you play it back again. Okay, so coming to some sort of closure here, a few slides left, we actually need new tools for design. So this is really important. And it's not enough to just put these tools there and say, here, I made this for you, use it. And don't come back, I have other things to do. That's what a lot of technologists do. Yeah, they are busy, right? They want to invent another thing and another thing and another thing, and the tools are just breadcrumbs on the way. But that is the wrong approach. So whenever we invent a new technology, we package it, we make it useful, we try to anticipate the needs. We need to be there. We need to make sure it actually lands. And that is not easy. That is part of the job. That is a large part of the job. Listening to people, getting that really difficult feedback that something is not there yet, or I don't know how it works, but it doesn't work. Huh? So these kind of things are really important. So basically the message is building and they will come is not true. Yeah? There's just too much out there. Yeah? So maybe 40 or 60 years ago, someone builds an amazing technology and everybody comes asking, but we're all overwhelmed. Yeah? Just finding stuff on Google is stressful for people. So it is really important to take care of the dissemination of the distribution of technology. And the better that works, the more successful it will be, the more used it will be, the more leverage you have, the more network effect can play a role. And maybe we also need to anticipate that things are developed differently than we might feel comfortable with. Yeah? So, and this is not just for engineers, it's also for designers. They love to play with a few layers, so the bottom layer. Just focus on there, get into the flow, and then work out something beautiful. In the end, a slice of it would have sufficed. And so it's really a different paradigm to work on just the whole stack and look at the vertical and see how you can get feedback as fast as possible. If you would want to get feedback from a very functional layer, well, you could do a unit test that would give you feedback, right? But if you want human feedback, you need to sort of let that technology bubble up. And then someone can actually say, well, that looks pretty good, but it doesn't work yet. Or my use case is different. And that's the information that you want. You want a clear specification, but the user matters. So how do you get that specification from that person? Well, you give something so that person can give you good feedback. That's really key. And this is like one level up, even higher. A lot of people say, in a defensive stance sometimes, that technology is neutral. We build it and it's neutral. It's not good, not bad, but everybody hopes it's good. The problem is that once technology is applied, once there is an impact, then you cannot say it's neutral. So that is really the point where a lot of things have to happen, a lot of things between the human and the technology. And that is what we see with AI. That was what we see with a lot of technologies that came before that. 10 years ago, 12 years ago, in design, everybody was amazed by a concept or a technology called Bluetooth. So they came around and were running around and jumping in the air. It was like, Bluetooth is going to save us all. It's incredibly insane. I mean, but yeah, this is the excitement with new technology. But we really need to think about how far that goes and what happens when it actually makes an impact. Okay, so a few takeaways. There are really new challenges that we see in design. And if we don't address them, then design becomes meaningless. And our way to address them is through education, through tools, through packaging, mediating technology in new ways. Giving designers the space to actually design, giving them materials to work with. We do this in design research and also in design practice. So there is a lot of research going on how we do these things, the methodology of using new materials, the boundaries of new materials, what is ethically possible or what should be possible, where should we draw the line, and quite often that should be earlier than we think. And I put all that stuff in here because I know that there are people from industry here, and it's really important to see this not for just design or design discipline, but for any industry that makes products that are eventually touching the human. It is very important to consider giving technology more time to mature, to be mediated, to sort of fall into the right place. And that's what design can help with, obviously. So this is it. I would like to thank you very much for listening, and perhaps you have some questions. Now's the time.
Okay, I think we have some time for questions because we started late. Anybody wants to give the first shot?
Fantastic talk. Thank you. I'm just wondering about when you think about interacting at a higher level, what you were talking about with IIP, for example, and the conflict that we have when we have multiple people trying to interact with intelligent systems. Sometimes we use kind of the lower level and the physical objects as ways to facilitate and, you know, essentially who gets the remote control problem. As you think about interacting at the higher level, how do you see technologies enabling, you know, a better facilitation across people, or, you know, enabling people to have their different say within the final outcome?
Thank you. That's a really good question. Actually, there are at least 2 people in our research group working on that. And if you ask me, I think we still need lower level technologies a lot, and probably more and better, emphasis on better than before, for sure. When you interact with an intelligent system, then what we currently do is we talk to an object, or we talk to a room, and then we hope that something picks up this command. And we use a certain protocol for that. So the human makes like 1, 2, maybe even 3 steps towards the technology, and the technology is just sitting there. It has been engineered, it's working fine. So, but maybe we need to reconsider how many steps the human needs to take to actually do that. And one of the ideas that were behind IIP was that we minimize the amount of interaction that is actually necessary. And one assumption that was behind this goal was also to say, let's consider the smart home, and let's consider how much accuracy and how much control, like fine-grained control, someone needs on the temperature. Yeah? So do people need to adjust the room temperature to 22.3 degrees? Or is it just fine to simply say, I'm cold? Yeah? So it's a very simple shift from absolute control to relative. You say, oh, just make it a bit warmer. And then if you have multiple people in the room, you don't want to ask them, so how many degrees do you want? How many degrees? How many? And then we take the mean and then set it. Yeah, that's too simple. So how can we find ways to balance between all these kind of needs? I'm not sure if this is going in the right direction still, but it is really about rethinking what is necessary in terms of interaction and how little we might just need. People are fine with a lot of things. People are flexible if they are not annoyed by stuff. And actually what we try to do is often, we try to give people interaction possibilities. And by doing that, by asking so much, we annoy people more than if we would just set the temperature and say, well, it's probably okay. And well, the truth is it's okay in most cases. So I can easily argue for less technology and less interaction, no problem, if that is done well. And that is really the point. Oh, thank you.
Any other question? If I may, I actually have something that I think is quite interesting, that because you have mentioned about the technology and ethical use of technology and where is the boundary and things. And in the United States, actually a lot of technology was invented for bad purposes first. And then somehow the technology has been adopted by, so because like in US, that DARPA is the biggest funder of a lot of projects. Even, for example, like the IoT, they started with the smart dust. Smart dust really is not for everybody to use. It's really designed for battlefield. And Boston Dynamics was also, doing something. So I don't know, in terms of all this thing, how do we actually use the bad technology for good things rather than use the good technology for bad things? How do you think about this too?
Okay, fundamental talk coming. No, okay, thank you for the question. I think it's really a really good question that we should ask ourselves all the time. Well, what I try to say is that people who make technology, they have their own impression that this is probably a good thing to make, and it should be used for good purposes. And then bad stuff happens, so maybe politics go in the way, or certain business interests come. Well, I can also maybe paint the European perspective. So in Europe, we have the GDPR, which is basically a general data protection law, and that basically, I think, has the goal to make massive data collection toxic. So data becomes something that is not the more the better and so on, and you just fill a silo up, and who has the biggest silo wins. I think the GDPR is really breaking with that pattern and trying to make companies especially, but also governments, conscious about that all the data in that silo belong to people. And the GDPR gives these people the explicit right to ask, what is there stored about myself? Is that correct? Let me edit this. Let me delete it. Let me ban you from collecting any more data on myself, which is super powerful. And if you think about the operations of a data collecting enterprise, 4 of these points are extremely hard to do at scale. Yeah? To make all these interfaces that people can review their own data, to authenticate them first, authorize them, etc., etc. Then they review the data, then they edit the data, then maybe they delete the data, and then what about the data that is actually in cold storage, and all these backups that are somewhere in the mountains? You have to delete that as well. You have to make sure that everything is gone, because there will be an audit and there will be hefty fines. So this is a very interesting perspective that a lot of people don't see, that potentially a whole ecosystem of companies, of businesses that are collecting data with the purpose of advertisement, they might just go away. They might just disappear. And they are fighting now very eloquently against this. But it's an interesting perspective that technology that is maybe made for the good of people is used for invasive ways, to say it carefully, and then weird things happen. So it's not that someone decided to invent I don't know, advertisement and then annoy everybody who browses a website worldwide, but it's like a reaction. It's a chain of reactions, and in the end that leads to a path that is maybe not desirable in the end. And yeah, sometimes we have to break that chain. So well, that's a small answer to a very, very big question.
Okay, because of time, I think that let's thank NtuEE70th for this wonderful talk. Thank you.
So we still have one very exciting talk before lunch, and it's going to be given by Professor Michael Tsai. He's a full professor in computer science at National Taiwan University now. So we are very proud to have Michael as part of our center, because he literally grew up with us. And
right.
So he's going to share his very exciting work on centimeter level visible light positioning and beyond. So I'll let Michael take over. Yeah.
Thank you. Thank you so much for the introduction. Okay, so a little bit change of pace. This is slightly more technical than the previous talk, but because of the time limitation and the fact that this is the last talk before lunch, I'll just keep it hopefully higher level. So a little bit about myself. I'm a professor in computer science and information engineering department here at NTU. My two main research areas are, one is related to light, how to use light for communication, and also for, most people call it localization, and we call it positioning. It's basically the same thing. My other area is about cars. So today we have a demo outside actually combining those two areas. We're basically using light to do communications between cars. We also have a poster on the stuff that I'm going to talk about today. So if you're interested in discussion a little bit more, feel free to stop by we don't really have a podium, our car is outside. Okay. So a little bit about the background of this line of research. I think most of the people here know a lot about location-based service, but the basic idea is that in many places like larger retail stores, Taipei Main Station, Taoyuan Airport, those large areas, I mean, users, they don't know how to get around. So if you have a phone in your hand and you have very accurate location information, then this app that get installed on your phone will be able to tell you how to get to a certain place, maybe go to a gate, go to the train platform, where to buy the tickets, go to a particular store to buy food, buy your lunch. Inside the store, you can do a little bit more. For example, if you have app and very, very accurate, like centimeter level error type of location information, then you can actually direct your customers to a product. For example, this product might be something this customer is looking for. It might be something that's on sale. So you can direct the customer to directly go to that rack and look for that particular product. So note that we're talking about the size of a rack and maybe also orientation information to direct exactly the customer to look at that product. Okay, so that means very, very accurate location information. And in addition, if we have those information in your app, the store might be doing a little bit more fancy stuff, maybe doing some customer behavior analysis, try to optimize the layout based on the hot zone inside the store. So there are a lot of things that you can do with this information. Now, traditionally, people do this with radio frequency signal. So most common scenarios, most common systems is using a lot of Bluetooth iBeacon. You just spread hundreds and hundreds of iBeacons in your environment, and hopefully that will give you good results. But it's not really giving you good results because of interference. Let me talk about the benefits of using lights, and then maybe you can compare existing technology with some of the technologies we are offering and see what's the real benefit. So first of all, we are offering really, really good accuracy. And there's a reason to that, because light's propagation mechanism is a lot simpler than radio frequency signal. It's directional, and usually it only works with line of sight. So for example, light within this room, if you step outside of the room, you pretty much don't get anything from a source inside here. So when there's blockage, when there's obstruction, you get no interference. So that's good and bad, but here it's good, because when you're in a different room, you only get signal from a source inside that room. Your signal is going to be very clean, it's easier to process, and that ended up will give you very, very good accuracy. Cost-wise, we're utilizing existing illumination infrastructure. So we have to have lights in every room, right, for illumination, for our eyes to see things. What we're trying to propose is just to replace some of those existing light sources with the one that supports positioning, and then you're done, okay? We're utilizing commodity device as the receiver, mostly camera, but if you're working with wearables, for example, or maybe AGV inside the factory, you can use even simpler sensor like a color sensor or a light sensor in your device. So today I'm going to talk about two different technologies, and I will just give you a peek of what the main component or concept we're using. So the first one is utilizing what we call polarized color light. And here's a video showing you how it works. So we have those two pieces of plastics. And then if we do something to the first piece, it's going to create color. But that color is only visible with the second piece of plastic film. And this plastic film is actually called polarization polarizer, linear polarizer. and you only see the color with the second piece of polarizer. You can even create this very, very complex color pattern that we are going to use in our system. So the idea is we're going to use this as the lampshade for existing light sources. The material to create this lampshade is actually very, very cheap and simple. So this linear polarizer has this very low cost that it described here. And we're actually using ordinary transparent tape to create that very complex color pattern. So hold on to that, and then let's take a look at the second thing. The other technology make use of what is called addressable LED tube. It's just a fancy name, but the idea is you will be able to control each one of the LED individually for its output intensity. If it's color, then you're controlling RNG and B intensities. So we're trying to make use of that to create the second indoor visible light positioning technology. So let's talk about the first one. Forgot to set the timer, so I don't know how much I've been into the talk. 7 minutes now, right? Okay, so the first technology, we're basically creating a lighting infrastructure that can augment inertial tracking. So we'll talk about that in a few slides. Prior works in this area, they often talk about using existing light sources and use that to send out some signal representing ID. So this is a technology very much similar to GPS. Each GPS will give you ID, right? So if you're outside, you capture a signal from a particular GPS, and then you use some signal processing techniques to know the distance to that GPS satellite, right? This is exactly the same. When you open up your camera, you look at the lights that you see in the images, you decode the ID from the image, and then you try to do triangulation or trilateration to get your position. So the downside of that is similar to GPS. You have to get at least four GPS satellites to be able to do positioning, right? 3D positioning. Same here. The camera's FOV has to be able to see more than 4 LED lights to be able to do indoor localization. But that is a very hard requirement. So imagine inside this room, if you turn on your phone's camera, you probably don't see that many luminaries inside the image. That means you have to deploy this special light sources very densely, and that means a lot of cost and difficulty in deployment. So when we designed this system, we set some objectives. The very first objective is to be able to provide positioning with a single luminary, a single LED source. And we want to do just very minimal modification to the luminary. We want the signal out of the luminary to be imperceptible signal to human eyes. Again, very, very accurate positioning results. The receiving device we want to use is just a simple color sensor. But you can also use camera if you want. Say inside your phone, you don't really have a color sensor, but you have a camera, so you can still use it as the receiver of our system. We want the update rate to be high enough so that even when people are walking or are moving, maybe an AGV inside a smart factory, you can still use this technology to get very accurate localization results. Now, our systems complements what is called inertial tracking. So IMU, I guess most of the people here are familiar with that. It consists of multiple types of sensor, accelerometers, gyroscope, and magnetometers. And each one of them measures the sensor information in 3 different axes. So with those sensor information, existing methods can give us the trajectory, estimation of the trajectory of the device that you have in your hand. So the idea is we integrate acceleration and angular velocity. So in the case of acceleration, we integrate it 2 times. In the case of velocity, we integrate 1 time, right? This does not give us very, very accurate result. Why? Because there's always noise in sensor data. As we integrate this data, noise start to accumulate. So after a while, maybe after 5 or 10 seconds, the accumulated errors start to become at meter level. So even more than 10 meters sometimes. So this is called sensor drift, right? And usually how people deal with this problem is they have to have some kind of landmark to reset the error once in a while, periodically. So that's what we want to do as well, using light. Okay, so let's talk a little bit about that polarized color light, a little bit, with a little bit more technical details. Ordinary light sources, it generates unpolarized light, meaning light waves oscillate in all different kinds of directions, okay? So if I put a linear polarizer in front of it, only light oscillating in that direction will get through, and you get what is called polarized light. Now, if I have white polarized light, what does that mean? That means there are different colors of light. So white lights composed of like red, green, and blue with a certain mixture, right? But they all oscillate in this direction. Now we pass that through something called optically anisotropic material. Basically that's transparent tape. After it passes through this material, different colors of light, it changes its polarization orientation. So it'll move by an angle. But this depends on the color of the light, which means wavelengths of the light. Okay, so now if you are looking at this light, what will you see? You still see white light because human eyes is not sensitive to the polarization direction of light. So you still see this mixture of light in different color with different orientation, but it's still white light, even if it changes. Okay, so now if we have a second piece of linear polarizer at the receiver, not in front of the light, at the receiver, then your eyes will see a certain color because now they're in different orientation. It'll, light that's not in the same orientation will get filtered out, so you only get a portion of the intensity for that color light. Eventually you get a mixture of that, and that's color. It's no longer white. Okay, so that's how we create polarized color light. Now if you change the orientation of this material, or you increase the thickness of that material, everything changes. How much angle it rotates for each color, it changes. So that means you'll get a different color at the receiver as well. Okay, the animation is a little bit slow, but I'm done with this slide. And that's all created by using a roll of transparent tape. So how do we use this as a lampshade? So we first create a grid-like structure, putting tapes with different layers, different orientation onto the linear polarizer. And then we put it in front of a light source. So polarized white light, it gets through this lampshade, and for different cell, it'll generate different polarized color, and it'll be projected onto the floor, and in different cell you'll get different color. This color is only visible to your color sensor, but not to human eyes. So if I'm looking at the floor here, I only see white light, uniform illumination, white light. Now if I have a Roomba with a color sensor on the top, also the second piece of polarizer in front of it, as it moves around the room, you'll see different color. Okay? And I think now you know how it works. As you see a sequence of color, you now have a pretty good idea of where you are within the room, within the pattern basically, but also within the room. It's basically relative positioning. You know where you are with respect to the light source. Now, why do we want to combine inertial tracking with this lighting infrastructure? So the right figure shows you, so the black dash trajectory, that's the ground truth. So inertial tracking usually gives you something like the other two. It's a little bit off, but you have a pretty good idea of where the device is going. It's just sometimes y or x distance is wrong. Sometimes longer, sometimes shorter. So what we do with this color cellular-like structure is to bring it back to be within the boundary of the cells. So for example, if you see this particular sequence of colors going through this and that and that and that, then you know the trajectory has to be within the boundaries of those sequence of cells. Initial sensors are sometimes good because you don't need any infrastructure for that. So it allows us to track large-scale movements. You can continue to track a device even when your light, your sensor don't see light. There's blockage maybe. Or maybe you don't use dense deployment. Sometimes you get out of the coverage of this light. However, you can continue to track your device. Now, color sensors is good because it's directional, and usually the projection on the ground is very accurate. It's not distorted. The cell boundary help us to contain the error, just like I said. And when you cross the boundary to a different cell, it basically gives you an opportunity to reset the error in inertial tracking. So that's the high-level idea. Now let's look at some of the video. So that's the positioning light. And on the floor, you see white light, right? Now, if you put the second piece of polarizer up there, just to show you how it looks like, now there's color, right? And the version we create that has 20 by 20 centimeter cell size on the floor. Of course, this can be changed. If you ask your student to do a little bit more work, maybe it's 10 by 10 or 5 by 5. You use different optics. It can be projected to a larger area, but then you might get a larger cell. Now, let me talk a little bit about the problems we have to solve in this system. The first one is when the receiver changes its orientation, you get different color, like the video shows. So that obviously doesn't work, right? You need to know how it looks like at a certain angle. So this is basically a theoretical optical theory problem. It's a theoretical optical problem. So we come up with this equation. There are a couple parameters we have to estimate. But the basic idea is after getting some training data, you can fit the curve pretty well to know the values of those parameters. Now you have this function, f of theta. Theta is the relative orientation between the transmitter and your receiver. So it doesn't matter what degree you have right now, you have a pretty good idea of what the color maps is going to look like. The second problem we're trying to solve is ambient interference. So at the receiver, you have a color sensor. Basically, that's intensity sensor in RNGMB. So the ratios between those intensities give you an idea of what kind of color you're looking at. The linear polarizer in front of it is at a certain angles. Now, you have light from the lampshade system going through the channel, polarized color light. So you get contribution from the lampshade system. But also, if you have some ambient light interference from the environment, you also get contribution from that source. Now, the intensity change, right? So the ratios between those three different intensity would be different. And then it's no longer accurate because now you're looking at a different color. So how do we solve this problem? The solution is to have co-located dual color sensors. So you have two color sensors at the same place, but the polarizer in front of it are in slightly different angles. So one is this angle, the other is perpendicular to that. How does this solve the problem? You still have this equation, but now you have two of them, right? Contributions from the lampshade system. Now, the intensity for the first sensor and the second sensor are not going to be the same because the polarizer orientation are different. But since the ambient light source generates unpolarized light, that means a uniform mixture of light in different polarization orientation. So the intensity that you get at the first color sensor and the second color sensor are going to be the same. So now if we subtract one from the other, we actually cancel out the ambient light term. Now, the remaining term is the differential color that you see from those two color sensors. It's not the same as the original color, but still some kind of color that we can work with. So using this as a solution, and finally we were able to implement the entire system. Maybe next, let's look at some of the performance numbers. The 2D accuracy is actually pretty good. Here we're comparing using just inertial tracking, which is the right curve, and using our light infrastructure, lampshade system, and inertial tracking. This is a CDF, probability distribution. X-axis is the accuracy, the error. So this is in log scale. But the median error, 2D error that you see when using our lampshade system is 4.3 centimeter, which is what I said, centimeter level accuracy. And it's more or less determined by the size of each cell. So remember I said 20 by 20 centimeter. If you're able to shrink it down furthermore, maybe you'll get even better accuracy. But when you're using only inertial tracking, inertial sensors, you get meter level accuracy. This is 90 percentile results, and it's almost the same, right? 8.1 centimeter versus 13 meters. So in the past couple of minutes, I was talking about this passive lampshade that you put in front of the light source. Earlier in this center, we also created a technology that actually puts an active lampshade in front of your light source. So this active lampshade is actually created with LCD on your laptop. It's just smaller and cheaper, lower resolution, and it's in grayscale. So the idea is liquid crystal can actually change the orientation, the polarization orientation of light. So it'll actually create a temporal pattern that your light sensor is able to see at the receiver. Same concept, if you have the second piece of polarizer, you will be able to see this intensity change, but otherwise, you will just see white light. The system's accuracy is still very, very good, 2.7 centimeter. And this is self-contained. This does not even need the inertial tracking that we talked about just a couple of slides ago. So this is a demo video, active lampshade in front of LED, and you don't see anything unless you put the second piece of polarizer in front of the receiver. So you see a sweeping pattern. If you're at a certain location, as you get scanned, you get a peak in your signal or a drop in your signal, and that will give you a pretty good idea of where you are within this 2D environment. And you see the student move the sensor a little bit. The estimation also moves with it. And all of this is done within maybe 1.5 meter by 1.5 meter plane. So the accuracy is still very, very close to centimeter level. I have 16 minutes. So I'll start to talk about the other, the second technology. So remember, the main component is what is called addressable LED tube, right? Now here are the design objectives of this second technology I'm going to talk about. Still, we want to use just one single lighting device to be able to provide positioning service. So you don't have to deploy it very densely. You just need to replace some of the existing illumination infrastructure to be able to provide localization or positioning service. In this case, we are trying to replace some of the existing fluorescent tube in your existing lighting. And we replace that with our tube. The receiver is a camera. So as you take pictures of what's up there at the ceiling, you will be able to do, again, centimeter level accuracy positioning. Human eyes will not be able to see the signal from the LED tubes. So how does it work? It'll based on we can individually control the brightness of the LEDs. So basically utilize that, and we use two different brightness level, high level and low level, to represent bits, and we use this to represent the ID numbers of a particular tube. Okay, and I think you can probably guess how it works. And then let's talk about it. So you're holding a film, walking inside the room. Perhaps the front camera will be able to take a picture of what's up there, and it will capture a positioning LED tube that we created. Now the next step is from this picture taken by the camera, you can decode the spatial pattern. And that pattern will tell you what's the ID of this LED. And with that information, we check with a built-in database, perhaps in your phone or perhaps on the cloud in a server. And you know, only in this room, I will be able to see this particular LED tube. And that will give you very coarse localization, right? Maybe it'll tell me I'm within this room 101 in Wally building, okay? We don't stop there. Based on what you see from the image, from the capture image, actually you can do fine-grained level localization. So based on the orientation, the size, and the location of the LED tube inside the image, you can do a little bit more, and that will give you even better, even more accurate estimation of the location. Now, the first problem we have to solve with this kind of design is we don't want to see the spatial pattern, right? So imagine some of the LEDs have higher brightness, some of the LED has lower brightness, but we don't want to see it like that. The solution we come up with is to have a complementary pattern. So for example, this particular LED does not come out. Okay, this particular LED has higher brightness. This one is its complementary pattern. It's going to be in lower brightness. Same for this one. This one has lower brightness, so the other one would have higher brightness. Now, we switch between those two patterns at a frequency of 125 Hertz, and that's higher than the limit of persistence of vision. So basically, human eyes see an average brightness level of the two, and you just see a uniform white pattern with the same intensity. But this also creates a problem, and it's related to how our camera works. So there's something that's called rolling shutter, right? So, and it sits inside most of the phone's camera today. How does it work? So when you take a picture, different rows of pixels are actually exposed to light at slightly different time. So, and it goes sequentially from row 1 to the last row. Global shutter camera does not do so. It captures light at exactly the same time, but it's more expensive. And that's why most of the cameras today still uses rolling shutter. How does that affect our system? So, for example, if you are trying to capture a fast-changing scenery, maybe a moving, well, humans actually don't walk that fast, maybe a train, and you will see actually a tilted version of that in your capture image. And that's only because you're capturing the scene at slightly different time. If we put this rolling shutter camera to capture this LED tube we just created, then this change of pattern between the normal one and the complementary one might happen as the rolling shutter camera go through different rows of pixels. So here's an example. We're trying to capture this normal pattern, and rolling shutter camera move through the entire LED tube, and at some point it changes to a different pattern, right? So what you capture is actually, the first part is going to be part of normal pattern, second part is going to be part of the complementary pattern, and this is what you get. It's a mixture of the two, and obviously if you decode that, then it's not going to be correct. I'm running out of time, right? Okay. So how do we solve this problem? It's very simple. You actually put two checking LEDs. So on one side you have preamble. So it's either it either has a bit 1 or a bit 0. The other one also has exactly the same bit with that. So when you take a picture, if you see those two bits are the same, that means they belong to the same pattern. If they are not the same, then that means when you're going through this LED tube at some point it changes to a different pattern, and you should drop that image and wait for the next turn. So using this approach, we solved the problem of rolling shutter camera. There are slightly more details, but I obviously don't have time to cover all of that. The last thing I want to talk about is this actually is pretty short if you think about how many LEDs you have in an LED tube. So what we get to do is to repeat this for multiple times in a single LED tube, and this gives us the benefit of even when you have some obstruction, or maybe your camera just does not have wide enough field of view to see the entire LED tube, you will still be able to decode the LED ID. Very quickly about how we do fine-grained positioning. So the idea is with the appearance of LED tube inside your image, you can actually do very, very good positioning. So I will just show you at high level how it works. Now, if we are directly below the LED tube, one end of the LED tube, imagine what you're going to see in your image. Okay, the answer is you're going to see this because you're directly below, so the center of the image is going to be one end of the LED tube. Now, we work starting from this scenario. If I move slightly away, let's say I'm not directly below now, I move away from that point. Now what are you going to see? Based on how much you move away from the below of the LED tube, you're going to also move away from the center point of the image. And now there's all kinds of mathematics which will actually give you a very good estimation of where you are based on the orientation, the size of it, and also how far you are away from the center point of the image. Okay, so that's how we can get from coarse level accuracy to fine-grained centimeter level accuracy. Now, here are some results that we can look at. So my student did experiments in 120 centimeter by 170 centimeter plane, and they measure the positioning error in a grid-like structure. So you see the size, the length of the vector here that represents the error. And you see everything is within that grid, so that means the level of error is always centimeter level. On the right side, again, you see a probability distribution. X-axis is the error, y-axis is the probability. So we see the median error to the error is only 4 centimeter, and the 90 percentile is at 7.5 centimeter. Okay, so two different kinds of technology. Both will give you very, very accurate results. Okay, so I am getting to the end of my presentation. We talk about how to use visible light for very accurate positioning, mostly indoor, but I believe in an outdoor setting, it'll also perform very well. Some of the benefits we talk about includes, for example, you can combine these functions with existing illumination infrastructure, and we use that to keep the cost very low. Optical signal is very simple to work with because of its simple propagation mechanism. It's line of sight only, it's directional, it does not escape visual obstruction, it just stays inside the room. That means very, very low interference. And working with that, that's why we can get very, very good accuracy. We work with commodity device. You use either a camera or you can have a simpler color sensor or light sensor if you want to work with a smaller device. Now we talk about two different technologies. One, work with polarized color light. Putting a lampshade in front of a light source, you create a pattern on the floor, and you can get very, very good accuracy. Now we have a different option. If you're not working with a point source, you're working with a tube, then you can replace some of the existing ones with our positioning tube. And then it's use spatial pattern to represent the LED ID. And finally, using the position, the orientation of the tube inside the image, you will be able to estimate very accurately where you are with respect to the light source. So I'll stop with the pictures of the lampshade and the LED tube. And I welcome any question. Thank you.
Okay, if you are not too hungry, we have time for maybe 1 or 2 questions.
Sorry, I'm an elementary school, so let me speak in Chinese in questions. 就是如果老师您可能用成一个学习的桌灯，那拍着这个学习的桌面，那是不是这个学生在他的学习素材上，不管是课本的，或者是平板的，或者各种文具的操控，我们是可以抓到他的学习行为？我想这样的话，这个技术是不是可能达得成？谢谢。
我想困难点是你需要在学生的手上去装一些接收光的感测器。对，那这个事情我觉得不管是成本上，或者是你要叫小朋友去做这件事，好像是另外一个研究。对，我不敢说不可能，我自己家里也有小朋友，也是小学的，但我想象我要请他手上戴一些手环等等的去抓他的行为，我觉得这是一个很有趣的题目。不过用我们现在的技术，可能还没有办法完全的做到这样。一样，就是你要抓他的手的行为或是动作的话，你一定要有一个接收器在他的手上。或许有一些其他的科技可以更容易的做到，不过也不排除啦，我们也可以试试看。谢谢。
One more question back there.
Thank you for the great talk. How small the errors can be pushed to using this technology, and what parameter determines the minimum errors?
When you talk about area, what area are you talking about?
No, I'm talking about, you're talking about your error is somewhere around centimeters.
Correct.
Can it be pushed to, for example, like millimeters and beyond? And what determines this resolution?
Right, so I guess you're talking about the first technology where we used a lampshade, correct? So like I said, it's basically determined on the cell size of the projection. So if you can have a very fine-grained cellular structure on your lampshade, then obviously you can get much better accuracy. But then it becomes I think a materials engineering problem, which is something that I know nothing about. But the way we create the lampshade is to ask the student to manually cut the tapes and put it on top of the polarizer. And that obviously does not work very well when you want to create a very fine-grained pattern. But I believe that's not really the barrier here.
Okay. Well, any more questions? If not, let's thank Michael for a wonderful talk.
Thanks.
So a couple of announcements. It's lunchtime, and everybody should have a lunch ticket, so you can get a lunchbox outside. And for center members and our collaborators, we can use the 201 room. This room, no food, no drinks. So for every one of our guests, you may use a room across the entrance. There are 3 class rooms in this building. So this is first floor. So once you get the lunchbox, just walk outside and walk straight to the other door. You will see all the rooms. Okay, and we will have guidance outside. And we will start our afternoon session after lunch at 1:30. 下午1点半是中文的，好，所以会有几个中文的演讲。那中文的部分会有蛮多都会是跟 要看的 demo 有关。好，那所以听完那个演讲之后，就会可以去看 demo 这样子。好，所以那个中间还会有一个小小的 break。OK， 好，那所以如果有什么问题再找我。那 otherwise we have our staff and everybody, so feel free to grab anybody if you have questions. Okay, thank you. I really appreciate everybody coming on Saturday for a very, I hope it's enriching time for everyone. Okay, thank you.